Q157. Volcanism has both positive and negative impacts on climate, the environment, and human life. Discuss. 15 marks, core demand of question. Explain the positive consequences of volcanism on the climate, environment, and human life. Explain the negative consequences of volcanism on the climate, environment, and human life. ANS. Volcanism is the geological process where molten rock, ash, and gases erupt from the Earth's interior, forming captivating volcanic features. Eruptions sculpt the landscape, create new geological formations, and can pose significant natural hazards. Studying volcanoes offers insights into Earth's dynamic nature, showcasing its ability for both destructive and constructive transformations. Positive consequences of volcanism. Climate regulation. Volcanic eruptions can release aerosols and gases into the atmosphere, which can reflect sunlight back into space, leading to temporary cooling effects. This can mitigate the effects of global warming by counteracting some of the heat trapped in the atmosphere. Soil fertility. Volcanic ash contains essential nutrients such as phosphorus, potassium, and sulfur, which enrich the soil when deposited during eruptions. This enhances soil fertility and promotes agricultural productivity in volcanic regions. Geothermal energy. Volcanic activity generates geothermal energy, which can be harnessed for various purposes, including electricity generation, heating, and hot spring resorts. This renewable energy source reduces dependence on fossil fuels and contributes to sustainable development. Tourism and recreation. Volcanic landscapes such as calderas, lava fields, and hot springs attract tourists and outdoor enthusiasts, stimulating local economies through tourism revenue and supporting recreational activities like hiking, sightseeing, and volcano monitoring. Formation of landforms. Various landforms are formed on the surface of the Earth by volcanic eruptions. Examples include volcanic cones, calderas, pyroclastic deposits, etc. Minerals. Most of the metallic minerals mined in the world, such as copper, gold, silver, lead, and zinc, are associated with magmas found deep within the roots of extinct volcanoes. Negative consequences of volcanism. Air pollution. Volcanic eruptions release sulfur dioxide, carbon dioxide, and other gases into the atmosphere, contributing to air pollution and respiratory problems for humans and animals. Ashfall can also contaminate air and water supplies, posing health risks to communities near active volcanoes. Environmental destruction. Lava flows, pyroclastic flows, and lahars, mud flows, can devastate surrounding ecosystems, destroying vegetation, habitats, and agricultural land. This loss of biodiversity and ecosystem services can have long-term ecological consequences. Natural hazards. Volcanic eruptions can trigger a range of natural hazards, including lava flows, ashfall, pyroclastic flows, lahars, and volcanic gases. These hazards pose risks to human life, infrastructure, and livelihoods, particularly in densely populated volcanic regions. Disruption of human activities. Volcanic eruptions can disrupt human activities, including transportation, agriculture, and tourism, causing economic losses and social upheaval. Evacuations, temporary displacement, and damage to infrastructure can strain local communities and economies, requiring costly recovery efforts. Global warming. While volcanic eruptions can temporarily cool the Earth's climate by emitting sulfur dioxide and other aerosols that reflect sunlight, they also release significant amounts of greenhouse gases, such as carbon dioxide and methane. Destruction of ozone layer. Volcanic eruptions release chlorine and bromine compounds, such as hydrogen chloride and bromine chloride, into the atmosphere. These compounds can catalyze the destruction of ozone molecules in the stratosphere, leading to the depletion of the ozone layer. Eventually, the impact of volcanoes varies, depending on factors such as the type of volcano, the size and intensity of the eruption, and the proximity of human populations and infrastructure. Effective monitoring, early warning systems, and disaster preparedness measures are essential for mitigating the impact of volcanic hazards and protecting vulnerable communities. Q158. Highlight the geological significance of the Pacific Ring of Fire, its impact on global tectonics, and the measures that countries around this region can adopt to mitigate the risks posed by its geological phenomena. 15 marks, core demand of question. Highlight the geological significance of the Pacific Ring of Fire. Discuss its impact on global tectonics. Suggest mitigation measures that can be adopted. ANS. The Pacific Ring of Fire is a vast geographical horseshoe-shaped region encircling the Pacific Ocean, renowned for its heightened seismic and volcanic activities. This area, characterized by frequent earthquakes and volcanic eruptions, plays a pivotal role in shaping Earth's geology and influencing global tectonic dynamics. Geological significance of the Pacific Ring of Fire. Plate boundaries. The Pacific Ring of Fire holds immense geological importance due to its association with multiple tectonic plate boundaries. Convergent, divergent, and transform boundaries intersect within this region, driving various geological phenomena. Convergent boundaries. Convergent boundaries foster subduction zones, where one tectonic plate descends beneath another. This process forms deep ocean trenches and volcanic arcs, often resulting in intense seismic activity and the creation of mountain ranges and volcanic islands. Divergent boundaries. Divergent boundaries give rise to mid-ocean ridges, where magma ascends from beneath the Earth's surface. As the magma cools, it generates new oceanic crust, leading to the continuous creation of the ocean floor and the expansion of ocean basins. Transform boundaries. Transform boundaries facilitate horizontal plate movement, where tectonic plates slide past one another. This lateral movement causes earthquakes along fault lines, as the accumulated stress is released when the plates finally overcome friction and shift abruptly. This movement of tectonic forces shapes Earth's crust and contributes to the dynamic nature of the Pacific Ring of Fire. Impact on global tectonics. Tectonic activity distribution. The Pacific Ring of Fire concentrates a significant portion of Earth's tectonic activity, influencing global seismicity and volcanic eruptions. This concentration of activity along plate boundaries contributes to the overall dynamics of Earth's tectonic system. Plate boundary interactions. The diverse plate boundary types within the Ring of Fire, including convergent, divergent, and transform boundaries, showcase a range of tectonic processes. These interactions play a crucial role in shaping Earth's lithosphere, driving plate movements, and redistributing crustal material on a global scale. Subduction zones and volcanism. Subduction zones along the Ring of Fire facilitate the descent of oceanic plates beneath. Continental plates, leading to the formation of volcanic arcs and deep-sea trenches. This subduction-driven volcanism not only shapes regional geology, but also influences global climate and atmospheric composition through gas emissions and ash dispersal. Hotspots. Hotspots are regions of intense volcanic activity that occur away from plate boundaries, often associated with mantle plumes, upwellings of hot, buoyant mantle material. Climate effects. Large volcanic eruptions can have global climate impacts by injecting sulfur dioxide and other gases into the atmosphere, which form aerosols which can lead to short-term cooling events known as volcanic winters, affecting global climate patterns and weather systems. Mitigation measures. Early warning systems. Governments can invest in advanced earthquake and volcano monitoring systems to detect seismic activity and volcanic eruptions promptly. Land use planning. Identifying and mapping high-risk areas prone to earthquakes, volcanic eruptions, or tsunamis can help in developing appropriate land use plans. Public awareness and education. Raising awareness among the population about geological hazards and educational programs can inform people about safety measures during earthquakes and volcanic eruptions. Regional cooperation. Collaboration among countries in the Pacific Ring of Fire region is crucial for sharing knowledge, data, and resources related to geological hazards and can improve the collective capacity to respond to disasters effectively. The Pacific Ring of Fire serves as a dynamic and geologically active region that plays a central role in the Earth's tectonic processes and has far-reaching implications for geology, seismology, and natural hazard management worldwide. Q159. Explore the classification of seismic waves and elucidate their role in enhancing scientific comprehension of the Earth's interior. 15 marks, core demand of question. Explore the classification of seismic waves. Elucidate how these waves help scientists to understand the interior of the Earth. ANS. Seismic waves are energy waves that traverse the Earth's interior following sudden energy releases like earthquakes, volcanic eruptions, and explosions. They hold key insights into the planet's composition and structure. By examining their characteristics and attributes, we can unravel the mysteries of Earth's hidden layers and geological processes. This exploration sheds light on seismic wave dynamics and their pivotal role in deepening our scientific understanding of the Earth's interior. Classification of seismic waves. Seismic waves are classified into two categories: body waves and surface waves. Body waves. P waves, primary waves. These are compressional waves. They cause the ground to move back and forth in the same direction the wave is traveling. They are the fastest type of seismic wave and can travel through both solid and liquid materials. S waves, secondary waves. These are shear waves. They cause the ground to move up and down, or side to side, perpendicular to the direction the wave is traveling. They can only travel through solid materials. Surface waves. L waves. These are a combination of P waves and S waves. They travel along the Earth's surface, and they are the slowest type of seismic wave. Surface waves can cause the most damage during an earthquake. R waves. These waves travel along the Earth's surface. They result from the interaction of P waves and S waves with the surface and are responsible for the rolling or undulating motion felt during an earthquake. Seismic waves help scientists understand Earth's interior. Determining Earth's layered structure. By analyzing the travel times and behaviors of P waves and S waves at different distances from an earthquake's epicenter, scientists can deduce the layered structure of the Earth, including the crust, mantle, and core. Identifying boundaries. Seismic waves reveal the existence of critical boundaries like Moho's discontinuity that separate the Earth's crust from the underlying mantle. The Gutenberg discontinuity marks the boundary between the outer core and the solid inner core. These boundaries provide essential information about the Earth's internal composition. Detecting Earth's core. S waves cannot pass through the Earth's liquid outer core, leading to a shadow zone where they are absent. The presence of this shadow zone helps scientists confirm the existence of the Earth's liquid outer core. Measuring density and composition. Seismic waves' velocities depend on the density and composition of the materials they pass through. Scientists use this information to infer the density and composition of the Earth's various layers. Studying Earth's interior temperature. The speed of seismic waves is influenced by temperature. By analyzing the wave velocities at different depths, scientists can estimate the Earth's temperature profile. External factors. External factors such as fluctuations in solar activity, cosmic radiation, and interactions with cosmic bodies, passing comets or asteroids, may influence the Earth's magnetic field and contribute to geomagnetic reversals. Variations in solar radiation and the solar wind can affect the Earth's magnetosphere, which in turn may influence the behavior of the geodynamo. Mantle plumes and hotspots. Some researchers have proposed that mantle plumes, which are upwellings of hot rock from the Earth's mantle, could play a role in triggering geomagnetic reversals. These plumes may cause disturbances in the Earth's mantle and core, leading to changes in the geodynamo and eventual reversal of the magnetic field. Cycles and periodicities. There is evidence to suggest that geomagnetic reversals occur in a cyclical or periodic manner, with intervals ranging from tens of thousands to millions of years. Some scientists have proposed that these cycles may be related to variations in the Earth's orbit, axial tilt, or other astronomical factors, although the exact mechanisms remain uncertain. Understanding geomagnetic reversals is not only crucial for unraveling the Earth's geological history, but also for assessing potential implications for modern technologies and ecosystems. Changes in the Earth's magnetic field can influence navigation systems, satellite communications, and even animal migration patterns. Therefore, continued research into this phenomenon is essential for both scientific inquiry and practical applications. Q161. Geomorphic processes bring changes to the surface of the Earth. In this context, discuss the types of endogenic geomorphic processes. 15 marks, core demand of question. Highlight how geomorphic processes bring changes to the surface of the Earth. Discuss the types of endogenic geomorphic processes. ANS. Geomorphological processes refer to the dynamic forces and chemical interactions that shape the Earth's surface, altering its configuration over time. These processes, driven by agents like magma, water, wind, sunlight, and biological organisms, can be classified as endogenic or exogenic. Endogenic forces originate from within the Earth, while exogenic forces act upon the surface from external sources. Geomorphic processes bring changes to the surface of the Earth. Geomorphic processes encompass a range of natural forces and interactions that shape and transform the Earth's surface over time. These forces, including erosion, weathering, deposition, tectonic activity, and biological influences, continuously modify the landscape and drive environmental evolution. For example, rivers carve valleys and canyons, while weathering shapes cliffs and boulders. Tectonic events like earthquakes and volcanic eruptions cause uplift and subsidence, reshaping terrains. Types of endogenic geomorphic processes. Diastrophic movements. These processes operate over extended periods, spanning thousands of years, and occur deep within the Earth's crust. They contribute to the formation of geological features such as mountains, plateaus, and valleys. This category encompasses both orogenic and epirogenic processes, which shape the Earth's surface through uplift and deformation. Epirogenic processes. These processes entail the elevation or deformation of substantial portions of the Earth's crust. They comprise vertical movements, which may entail both upward and downward shifts, contributing to the formation of continents. Orogenic processes. It encompasses the creation of mountains via folding, impacting elongated and narrow regions of the Earth's crust. During this process, the crust undergoes significant deformation, resulting in the formation of folds. Sudden movements. Characterized by swift occurrences, these events unfold relatively quickly, exhibiting destructive tendencies. Examples include earthquakes and volcanic eruptions. Volcanism. This process involves the ascent of molten rock, magma, towards the Earth's surface, resulting in the formation of diverse volcanic landforms. For example, volcanic mountains like Mount Vesuvius in Italy and volcanic plateaus, such as the Deccan Plateau. Q162. Earthquakes. Manifesting as sudden releases of energy, earthquakes generate waves due to plate interactions, rock displacement, and human activities like explosions or reservoir construction. These seismic waves can lead to ground shaking, fissure formation, and valley development, often causing significant destruction. In forecasting the future, understanding endogenic geomorphic processes remains pivotal for comprehending the Earth's ongoing transformation. As technology advances, predictive modeling and monitoring systems will likely enhance our ability to anticipate geological events, contributing to more effective disaster mitigation strategies and sustainable land management practices. Volcanoes play a significant role in shaping the Earth's surface and impacting the environment and human society. In this context, delineate the geological processes and factors that lead to volcanic eruptions. 15 marks, core demand of question. Discuss the role of volcanoes in shaping the Earth's surface. Highlight volcanic impact on the environment and human society. Delineate the geological processes and factors that lead to volcanic eruptions. ANS. Volcanoes play a pivotal role in shaping the Earth's landscape, environment, and human civilization. These geological phenomena stem from intricate processes influenced by tectonic plate movements and the behavior of magma beneath the Earth's surface. For example, the eruption of Mount Pinatubo in 1991 caused significant environmental changes and socio-economic disruptions in the Philippines. Role of volcanism in shaping the Earth's surface. Topographic modification. Volcanic eruptions eject lava, ash, and volcanic debris, altering the Earth's surface topography. Over time, repeated eruptions build volcanic landforms such as cones, calderas, and lava plateaus, contributing to the diverse terrain on the planet. Formation of new land. Volcanic activity creates new land masses through the accumulation of lava flows. For example, islands like Hawaii and Iceland are formed entirely from volcanic eruptions, showcasing the transformative power of volcanic processes in shaping the Earth's surface. Erosion and sedimentation. Volcanic materials, including ash and pyroclastic flows, erode and redeposit, influencing sedimentation patterns and landform evolution. Volcanic landscapes exhibit unique erosional features like valleys, canyons, and volcanic craters, highlighting the dynamic interplay between volcanic activity and surface processes. Impact of volcanism on environment. Air quality. Volcanic eruptions release gases and ash into the atmosphere, affecting air quality and posing health hazards. For example, in 2010, the eruption of volcano in Iceland released large amounts of ash and sulfur dioxide into the atmosphere, leading to widespread air travel disruptions across Europe and affecting air quality in nearby regions. Climate change. Volcanic aerosols can temporarily cool the climate by reflecting sunlight, influencing weather patterns and global temperatures. For example, the 1991 eruption of Mount Pinatubo in the Philippines injected millions of tons of sulfur dioxide into the stratosphere, forming aerosols that reflected sunlight. Ecosystem disturbance. Lava flows and ash deposits alter habitats, disrupt ecosystems, and affect biodiversity. For example, the eruption of Mount St. Helens in 1980 caused widespread destruction of forests and habitats in the surrounding area. Impact of volcanism on human civilization. Hazards to health. Volcanic eruptions can lead to respiratory issues, eye irritation, and skin problems due to ash and toxic gases. For example, during the 2018 eruption of Kilauea in Hawaii, residents experienced respiratory problems and skin irritation due to high levels of sulfur dioxide gas and volcanic ash in the air. Property damage. Lava flows, ashfall, and lahars can damage infrastructure, homes, and agricultural lands, causing economic losses. For example, the eruption of Mount Merapi in Indonesia in 2010 resulted in significant property damage, with lava flows destroying houses, roads, and agricultural fields in nearby villages. Social disruption. Evacuations, displacement, and loss of livelihoods disrupt communities, leading to social and economic challenges. For example, the eruption of Mount Nyiragongo in the Democratic Republic of the Congo in 2002 forced thousands of people to evacuate their homes, leading to social unrest. Geological processes and factors leading to volcanic eruptions. Plate tectonics. Most volcanic activity occurs at plate boundaries, where tectonic plates interact. There are three main types of plate boundaries where volcanoes can form. Divergent boundaries. At divergent boundaries, tectonic plates move apart, creating gaps that allow magma to rise from the mantle, forming new oceanic crust and mid-ocean ridges. Transform boundaries. Tectonic plates slide past each other, and the resulting friction can lead to volcanic activity, although it is less common compared to the other boundaries. Convergent boundaries. When two tectonic plates collide, one may be forced beneath the other in a process called subduction. This action creates deep-sea trenches and generates intense heat and pressure, leading to the melting of rock, which then rises as magma, potentially resulting in volcanic arcs. Magma composition. The type of magma, basaltic, andesitic, or rhyolitic, greatly influences the eruption style. High-viscosity magma, like rhyolitic, tends to trap gas and build pressure, leading to more explosive eruptions. Gas content. Dissolved gases, especially water vapor, carbon dioxide, and sulfur dioxide, play a crucial role in eruption dynamics. As magma rises, pressure decreases, causing gases to explode from the melt. The study of volcanic processes and their consequences is vital for understanding Earth's dynamic nature and safeguarding human society and the environment. By unraveling the complexities of volcanic activity, scientists can develop strategies for mitigating risks and enhancing resilience in the face of future volcanic eruptions. Q163. Discuss the geophysical characteristics of the Circum-Pacific Zone. 10 marks core demand of question. Discuss the geophysical characteristics of Circum-Pacific Zone. ANS. The Circum-Pacific Zone, commonly referred to as the Ring of Fire, is a geologically dynamic belt encircling the Pacific Ocean. Renowned for its heightened tectonic activity, the region experiences frequent seismic events, including earthquakes and volcanic eruptions, contributing to the formation of various geological features and landscapes. The geophysical characteristics of Circum-Pacific 1. Tectonic plate boundaries. The Circum-Pacific Zone is the convergence zone of several tectonic plates, including the Pacific Plate, North American Plate, Philippine Sea Plate, etc. These plates interact along their boundaries, leading to complex geological processes. Subduction zones. One of the prominent features of the Circum-Pacific Zone is the presence of numerous subduction zones. In a subduction zone, an oceanic plate is forced beneath a continental or another oceanic plate, creating deep ocean trenches and volcanic arcs on the overriding plate. Earthquake and volcanic activity. Volcanic activity in the Circum-Pacific Zone results from tectonic plate convergence and subduction. This process forms volcanic arcs such as the Andes, the Cascade Range, and the Aleutian Islands. The region is prone to earthquakes, caused by plate movements along boundaries. For example, the 2011 Tohoku earthquake in Japan. Hotspots. Apart from plate boundaries, the Circum-Pacific Zone also hosts several hotspots, which are stationary sources of volcanic activity. For example, the Hawaiian Islands are formed by a hotspot. Formation of the Pacific Ring of Fire. The Circum-Pacific Zone is also called the Pacific Ring of Fire because of the continuous chain of volcanoes and seismic activity that encircles the Pacific Ocean. This geologically dynamic area represents about 75% of the world's active and dormant volcanoes. Geological hazards. The geophysical characteristics of the Circum-Pacific Zone make it highly susceptible to geological hazards, including volcanic eruptions, earthquakes, landslides, and tsunamis. These hazards pose significant risks to human populations, infrastructure, and the environment, necessitating comprehensive monitoring, preparedness, and mitigation efforts. The Circum-Pacific One exhibits significant geophysical characteristics, resulting in substantial geological activity and hazards, such as earthquakes, volcanic eruptions, and tsunamis. Understanding these features is crucial for safeguarding the safety and resilience of the communities inhabiting this region. Q164. Define volcanic hotspots and expound upon their key characteristics. 10 marks, core demand of question. Define volcanic hotspots along with the examples. Shed light on the key characteristics of volcanic hotspots. ANS. Volcanic hotspots are permanent and localized regions of intense volcanic activity on Earth's surface, typically found in the interior of tectonic plates, far from convergent and divergent plate boundaries, where magma rises from the mantle to create volcanoes and geothermal features. Around 40 to 50 volcanic hotspots are known to exist around the world. Some examples include the Iceland hotspot, the Afar hotspot, and the Louisville hotspot. Key characteristics of volcanic hotspots. Origin. Hotspots, such as the Galapagos Islands, Reunion Island, and Iceland, are believed to stem from deep-seated mantle plumes, where hot material ascends from the Earth's mantle. This elevated heat flow causes magma to rise to the surface, leading to volcanic eruptions. Persistent volcanism. Hotspots exhibit prolonged and consistent volcanic activity over millions of years, leading to the formation of long volcanic chain or island chains. For example, the formation of a volcanic island chain above the Hawaiian hot spot beneath the Pacific Plate has been occurring for at least 70 million years. Volcanic island chains. Volcanic hotspots often give rise to linear chains of volcanic islands or seamounts. These chains are the result of the consistent eruption of magma from a fixed mantle plume hotspot, while the overlying tectonic plate moves gradually. For example, the Emperor Hawaiian Seamount Chain, located over the Hawaiian hotspot in the Pacific Ocean. Lack of tectonic plate boundaries. Unlike most volcanoes, which form at plate boundaries, hotspot volcanoes often emerge within a plate, away from tectonic plate boundaries. Also, volcanic hotspots have a relatively fixed or stationary source of magma deep within the Earth's mantle, unlike tectonic plate boundaries. For example, Reunion Island serves as an example of an intraplate volcanic hotspot. Aging of volcanoes. Volcanic islands or volcanoes formed by hotspots tend to become older as you move away from the current hotspot location. This results in a progression from young, active volcanoes to older, eroded ones. For example, the Hawaiian Islands display this aging pattern, with the Big Island, Hawaii, being the youngest and the northwestern Hawaiian Islands being much older and eroded. Other geological activities. Hotspots can also manifest distinctive geological activities like hot springs, geysers, and unique geological features in addition to volcanic eruptions. For example, Yellowstone National Park, U.S., is situated over the Yellowstone hotspot and features geysers such as Old Faithful, hot springs, and geothermal activity alongside its famous volcanic history. Volcanic hotspots are enigmatic geological phenomena that offer invaluable insights into Earth's geological evolution and deep interior processes. By unraveling the intricacies of these hotspots, we can enhance our comprehension of our dynamic planet, with far-reaching implications for both scientific understanding and environmental stewardship. Q165. The Pacific Ring of Fire is known for its intense volcanic and seismic activity. Discuss the factors responsible for the high level of tectonic activity in this region and its significance in global geology. 15 marks, core demand of question. Shed light on the factors responsible for the high level of tectonic activity in this region. Discuss its significance in the global geology. ANS. The Pacific Ring of Fire, also known as the Circum-Pacific Belt, is a 40,000-kilometer, 24,900-mile, long horseshoe-shaped stretch encircling the Pacific Ocean. Within this dynamic region, more than 450 volcanoes, constituting 75% of Earth's total, punctuate the landscape, while nearly 90% of the world's earthquakes reverberate through its terrain, bearing witness to the remarkable intensity of volcanic and seismic activities. Factors responsible for the high level of tectonic activity in the Pacific Ring of Fire. Tectonic plate boundaries. The Ring of Fire coincides with the boundaries of several tectonic plates, including the Pacific, Cocos, Nazca, Philippine, North American, Indian, Australian, and others. These plates are either colliding, diverging, or sliding past one another, leading to stress and strain in the Earth's crust, resulting in earthquakes and volcanic activity. For example, the collision of American and Pacific plates and the subduction of the Pacific plate below the Asiatic plate are the primary causes of volcanic activities in this region. Subduction zones. In the subduction zones of this region, oceanic plates are forced beneath continental plates or other oceanic plates. This process generates tremendous heat and pressure, causing the subducted plate to melt and form magma. The rising magma can lead to the formation of volcanoes along the convergent plate boundaries. For example, the subduction of the Pacific plate beneath the North American plate has given rise to the Cascade Range volcanoes in the Pacific Northwest of the United States. Plate fragmentation. The Ring of Fire has fragmented plate boundaries which create complex geological features and multiple zones of stress and deformation, leading to a higher likelihood of earthquakes and volcanic eruptions. For example, the Aleutian Islands in Alaska. Hotspots. Presence of hotspots in this region causes an upwelling of hot mantle material that can melt the overlying crust and create volcanic activity. For example, the Hawaiian Islands are the result of a hotspot beneath the Pacific plate. Pacific Ocean Basin. The vastness of the Pacific Ocean, which covers more than 60 million square miles, allows for the accommodation of plate movements and interactions over a wide area. This large basin provides the necessary geological space for the diverse tectonic activities observed in the Ring of Fire. Significance of the Pacific Ring of Fire in global geology. Tectonic plate interactions. The Ring of Fire is a direct result of the interactions between multiple tectonic plates, including subduction zones, transform faults, and divergent boundaries. These interactions shape the Earth's lithosphere and crust, making it a natural laboratory for studying plate tectonics, one of the fundamental theories in geology. Volcanic activities. This region hosts over 75% of the world's active and dormant volcanoes, showcasing the Earth's internal heat and molten material movement. The intense volcanic activity contributes to the formation of landmasses, such as the Japanese archipelago, and influences both local and global climate patterns. Island arcs and mountain chains. The Ring of Fire has distinctive geological features, like volcanic island arcs and mountain chains, formed as a result of plate subduction and uplift processes. For example, the Andes Mountains in South America and the Japanese archipelago are the outcome of plate interactions within the Ring of Fire. These geological formations have significant implications for local ecosystems, weather patterns, and human settlements. Mineral resources. Volcanic activity in the Ring of Fire can bring valuable mineral resources to the surface, making this region a hotspot for mining and resource extraction. Deposits of precious metals such as gold and silver, as well as important industrial minerals like copper, molybdenum, and other metals, can be found in this region. Geological hazards and preparedness. The Ring of Fire poses both opportunities and challenges for human societies. While it provides fertile soils for agriculture and geothermal energy resources, it also presents significant geological hazards, including volcanic eruptions, tsunamis, and earthquakes. Understanding the geological processes in this region is crucial for disaster preparedness, early warning systems, and resilience building in affected communities. Scientific research. The Ring of Fire is a hot spot for scientific research in geology, seismology, and volcanology. Scientists study this region to gain insights into the Earth's interior, the mechanisms of volcanic eruptions, and the behavior of tectonic plates. Findings from research conducted within the Ring of Fire have broader applications in understanding global geological processes. The Pacific Ring of Fire, characterized by its intense volcanic and seismic activity, stands as a testament to the dynamic forces at play within our planet. While this region poses geological hazards, it also provides opportunities for scientific research, resource utilization, and sustainable development. Therefore, its significance in global geology extends beyond its natural wonders to encompass our ability to coexist with the dynamic Earth and harness its resources while preparing for potential disasters. Q166. Compare and contrast the different aspects of plains and plateaus, and explain how their formations are shaped by the interplay of diverse factors. 15 marks, 250 words, core demand of question. Provide the similarities between the plains and plateaus. Discuss the difference between these two landscapes. Describe the various factors responsible for the formation of plains. Write about the diverse factors responsible for the formation of plateaus. ANS. The Earth's surface is a canvas of diverse landscapes, shaped over millions of years by geological processes and natural forces. Two prominent landforms that stand in contrast yet share unique features are plains and plateaus. For example, Indo-Gangetic Plains and Tibetan Plateau. Similarities between the plains and plateaus. Formation. Both plains and plateaus form through geological processes. For example, the Colorado Plateau uplifts due to tectonic forces, while the Mississippi River Basin forms from sediment deposition. Diverse ecosystems. Both have diverse ecosystems and habitats. For example, the Great Plains house diverse ecosystems such as grasslands, forests, and wetlands, supporting a variety of wildlife like bison and various bird species, i.e. Dudwa National Park. On the other side, the Deccan Plateau features habitats ranging from dry scrublands to forests, providing a home to tigers and elephants, i.e. Tadoba Unthari Tiger Reserve. Human settlements. Both plains and plateaus are significant for human settlements and agriculture. For example, the Indo-Gangetic Plain is densely populated and agriculturally productive, while the Brazilian Plateau, especially the Brazilian highlands, also supports human settlements and agriculture. These highlands support most of 190 million population of Brazil. Economic importance. Both offer valuable resources and economic opportunities. For example, North China Plain is a major agricultural region, producing wheat and rice, whereas Andean Plateau has rich mineral resources, like copper and gold, contributing to the economy. Tourism and recreation. Both plains and plateaus attract tourists for their unique landscapes and recreational activities. For example, the Serengeti Plain is a popular tourist destination known for wildlife and migration, while the Colorado Plateau draws tourists to explore its national parks, including the Grand Canyon. Key differences between the plains and plateaus. The interplay of diverse factors in shaping formations of plains. Deposition of sediments. Sediments eroded from mountains and highlands are transported and deposited on low-lying areas, gradually building up the flat or gently rolling topography of the plains. For example, the Indo-Gangetic Plain in South Asia is a prime example of a plain formed by the deposition of sediments carried by rivers like the Ganges and the Brahmaputra. Glacial activity. Glaciers erode and transport massive amounts of debris, which are later deposited as the glaciers recede, leaving behind a flat or gently undulating landscape known as glacial plains. For example, the vast expanse of the northern European plain, including parts of Germany, Poland, and the Netherlands, was shaped by the action of glaciers during the last ice age. Tectonic movements. Plate movements can cause subsidence or uplifting of large areas, creating basins that eventually fill with sediments. For example, the uplift of the Rocky Mountains and the subsidence of the Western Interior Seaway led to the formation of the Great Plains in North America. River delta formation. River deltas are specific types of plains formed at the mouths of rivers where they meet large bodies of water, such as oceans or seas. The deposition of sediment carried by the river results in the creation of vast and fertile delta plains. For example, the Mississippi River Delta in the United States, where the Mississippi River empties into the Gulf of Mexico, is a prime example of a delta plain. Erosion and weathering. The gradual breakdown and removal of rocks and soil by wind, water, and other natural agents contribute to the flatness and evenness of some plains. For example, the Nullarbor Plain in Australia is a vast arid region that has been shaped by millions of years of erosion and weathering. The interplay of diverse factors in shaping formations of plateaus. Tectonic plate movements. Plateaus are often formed due to the collision or separation of tectonic plates. When plates converge, it can result in uplifting and deformation of the Earth's crust, leading to the formation of high plateaus. For example, the Tibetan Plateau, also known as the roof of the world, was formed due to the collision of the Indian and Eurasian tectonic plates. Volcanic activity. Plateaus can be formed by volcanic eruptions, where vast amounts of lava and volcanic materials are ejected onto the Earth's surface. The accumulation of volcanic materials over time can create large, elevated plateau regions. For example, the Deccan Plateau in India was formed by massive volcanic eruptions during the Cretaceous period, resulting in thick layers of basaltic lava. Erosion and uplift. Uplifts due to tectonic forces can create elevated areas, while erosion by rivers and glaciers gradually levels the surrounding landscape. For example, the Colorado Plateau in the United States was uplifted by tectonic forces, and over millions of years, the Colorado River and its tributaries have eroded the plateau, creating the Grand Canyon and other canyon systems. Sedimentary deposition. In some cases, plateaus are formed by the accumulation of sedimentary rocks over millions of years. Sediments from nearby mountains or surrounding areas can be deposited on a plateau, leading to its formation. For example, the Colorado Plateau is also an example of sedimentary deposition. Over time, sediments from eroding mountains were carried by rivers and deposited on the plateau, forming sedimentary layers. Climate and weathering. Climate and weathering processes can influence the formation of plateaus. Harsh climatic conditions can lead to slow weathering of rocks, contributing to the gradual rise of plateaus. The distinct features and formation processes of plains and plateaus showcase the intricate interplay of diverse factors, leaving a lasting impact on ecosystems, human societies, and the Earth's natural history. By understanding these landforms' complexities, we can foster a deeper appreciation for the wondrous diversity that our world has to offer. Q167. Explore the profound impact of endogenic processes on the Earth's crust, as the very fabric of our planet is shaped by these hidden forces from within. Unravel the distinct characteristics that set endogenic processes apart from their exogenic counterparts. 15 marks, 250 words, core demand of question. Discuss the impact of endogenic processes on the Earth's crust. Contrast the endogenic processes and exogenic processes. ANS. Endogenic processes refer to geological processes and phenomena that originate from within the Earth's interior and are driven by internal forces, such as heat and pressure. These processes mainly involve tectonic activities like plate movements, mantle convection, volcanic eruptions, earthquakes, and mountain building. Together with exogenic forces, they shape the Earth's surface and influence the planet's geology. Impact of endogenic processes on the Earth's crust. Volcanism and landscape transformation. Endogenic processes generate magma, leading to volcanic eruptions. This creates new landforms and adds layers of lava to the Earth's surface. For example, Mount St. Helens eruption in 1980, shaping the landscape of Washington State, USA. Earthquakes and faulting. Alters the Earth's crust through forming fractures and displacements, as exemplified by the San Andreas Fault in California, USA. Mountain building. Converging plates push against each other, leading to the formation of mountain ranges. Moreover, these geological features impact climate and influence erosion patterns. For example, the Himalayas formed by the collision of the Indian and Eurasian plates. Rift valleys. Diverging plates create rift valleys, where the Earth's crust is stretched and thinned. For example, the East African Rift, which is gradually splitting the African continent. Subduction zones. When one tectonic plate is forced beneath another, it creates subduction zones. These zones influence volcanic arcs and deep-sea trenches. For example, the Aleutian Islands in Alaska, formed by subduction along the Aleutian Trench. Crustal differentiation. As magma cools and solidifies, minerals separate, leading to crustal differentiation. This process forms different types of rocks and mineral deposits. For example, the formation of granite through the cooling of magma beneath the Earth's surface. Geothermal energy. Endogenic processes generate geothermal energy from the Earth's internal heat. This renewable resource can be harnessed for electricity production and heating. For example, Geothermal power plants in Iceland, using the country's volcanic activity for energy. Crustal uplift and subsidence. Endogenic forces cause parts of the crust to uplift or sink. This influences landscapes, river systems, and coastal areas. For example, the uplift of the Colorado Plateau in the USA, creating the Grand Canyon. Characteristics of endogenic processes differentiating them from their exogenic counterparts. Origin. Endogenic processes originate within the Earth, involving movements and interactions of tectonic plates, mantle convection, and volcanic activity. In contrast, exogenic processes originate on the Earth's surface and are influenced by external forces like water, wind, and ice. Energy source. Endogenic processes are primarily driven by the Earth's internal heat and the energy generated in the mantle, resulting in movements of rocks and magma. On the other hand, exogenic processes are driven by the sun's energy, which fuels the movement of water, wind, and ice. Type of material involved. Endogenic processes involve the movement of rocks and magma within the Earth's crust. These processes lead to geological phenomena, such as earthquakes and the formation of mountains and volcanoes. Exogenic processes, in contrast, involve the movement of water, wind, and ice, which shape the Earth's surface through erosion, weathering, and sedimentation. Rate of change. Endogenic processes are typically slow and gradual, while exogenic processes can be rapid and sudden. Scale of change. Endogenic processes can cause large-scale changes to the Earth's crust and the arrangement of continents, leading to the formation of mountain ranges and ocean basins over millions of years. Exogenic processes, in contrast, typically cause smaller-scale changes, shaping individual landforms such as valleys, canyons, and sand dunes over shorter time frames. Landforms. Mountains and plateaus like Himalayas and Pamir formed by endogenic forces versus sand dunes and river deltas like Ganga-Brahmaputra Delta formed by exogenic forces. To conclude, it is crucial to recognize the significant impact of endogenic processes on the Earth's crust and the unique characteristics that differentiate them from exogenic processes. The understanding of these forces will enable us to better comprehend the dynamic geological processes shaping our planet. Q168. Describe effusive volcanic eruptions and outline their characteristics. Subsequently, compare and contrast effusive volcanic eruptions with explosive volcanic eruptions. 15 marks, 250 words, core demand of question. Outline the characteristics of effusive volcanic eruptions. Provide the similarities between the effusive volcanic eruptions and explosive volcanic eruptions. Differentiate between the effusive volcanic eruptions and explosive volcanic eruptions. ANS. Effusive volcanic eruptions are intricate and sustained geological phenomena typified by the uninterrupted and non-explosive extrusion of low-viscosity lava onto the terrestrial crust. During these eruptions, magma with low gas content ascends to the surface, enabling the lava to flow effortlessly and form extensive lava flows. An example is the ongoing activity at Hawaii's Kilauea volcano. Characteristics of effusive volcanic eruptions. Non-explosive. Effusive eruptions are typically non-explosive, as they involve the steady extrusion of lava onto the surface. For example, the ongoing volcanic activity at Mount Etna in Italy. Low-viscosity lava. Effusive eruptions are fueled by magma with low-viscosity fluidity, allowing the lava to flow easily and smoothly over the Earth's surface. For example, the volcanic activity at Iceland's volcanoes, such as those in the Krafla volcanic system, which produce low-viscosity lava that can flow smoothly without much friction. Lava flows. The lava emitted during effusive eruptions forms lava flows, which can cover extensive areas and create new land as they cool and solidify. For example, the Holuhraun eruption in Iceland in 2014-2015, where large lava flows covered an area of over 84 square kilometers. Shield volcanoes. Effusive eruptions are often associated with the formation of shield volcanoes, which have broad, gently sloping profiles due to the accumulation of successive lava flows. For example, Mauna Loa in Hawaii is a classic example of a shield volcano. Lava plateaus. In some cases, effusive eruptions can lead to the formation of extensive lava plateaus, which are large, flat areas covered by thick layers of lava. For example, the Columbia River Basalt Group in the northwestern United States is a prominent lava plateau formed by numerous effusive eruptions. Continuous activity. Effusive eruptions can last for extended periods, with lava steadily flowing from the volcanic vent. For example, the Puyu'u eruption on Kilauea volcano in Hawaii, which lasted from 1983 to 2018, producing continuous lava flows for over 3 decades. Comparison of the effusive volcanic eruptions with explosive volcanic eruptions. Similarities. Magma origin. Both eruptions involve rising magma from Earth's mantle through volcanic conduits. For example, Mount St. Helens experienced both effusive and explosive eruptions. Volcanic venting. Both release materials through vents or fissures. For example, the 2018 Kilauea eruption had both effusive lava flow and explosive ash emissions from the same vent. Gas release. Both emit volcanic gases with environmental impacts. For example, in the 1991 eruption of Mount Pinatubo in the Philippines, there were both effusive and explosive phases, causing cooling due to released gases and ash. Tectonic settings. Both occur at convergent boundaries, divergent boundaries, or hotspots. For example, the Galapagos Islands had both effusive and explosive eruptions on different islands. Formation of volcanic cones. Both contribute to forming volcanic cones and mountains. For example, Arenal volcano in Costa Rica has a symmetrical cone from both types of eruptions. Hazards. Both pose risks to communities and infrastructure. For example, the 1980 Mount St. Helens eruption had both effusive and explosive phases, resulting in devastating pyroclastic flows that destroyed surrounding forests and infrastructure. Impact on climate. Both influence weather and global temperatures. For example, the effusive Laki eruption in 1783-1784 and the 1991 explosive Mount Pinatubo eruption both released sulfur dioxide into the atmosphere, resulting in cooling of the climate. Aspect effusive eruptions. Explosive eruptions type of magma low viscosity, basaltic, as exemplified during the 2018 Kilauea eruption in Hawaii high viscosity, andesitic or rhyolitic, as exemplified during the 1991 Mount Pinatubo eruption in the Philippines. Eruption style, continuous lava flows, sudden and violent bursts of volcanic material and ash gas content relatively low as seen during the 2014-2015 Hularan eruption in Iceland, relatively high as seen during the 1883 eruption of Krakatoa in Indonesia. Volcanic landforms shield volcanoes with gentle slopes as exemplified by the Mauna Loa in Hawaii, stratovolcanoes with steep slopes as exemplified by the Mount Vesuvius in Italy. Hazards. Lower immediate hazards, slow-moving lava flows, as seen in the case of ongoing eruptions at Kilauea volcano in Hawaii. Higher immediate hazards, pyroclastic flows, ashfall lahars, as exemplified by the 1985 eruption of Nevado del Ruiz in Colombia. VI, volcanic explosivity index, lower values, usually 0 to 2, higher values, usually 3 to 8. Frequency more frequent. For instance, persistent eruptions of the Stromboli volcano less frequent. For instance, the eruption of Krakatoa, 1883, in Indonesia. Geological impacts. Formation of extensive lava plateaus and basalt plains, as exemplified by the Deccan Traps in India. Collapse of volcanic edifices, resulting in calderas. For instance, the eruption of Mount Mazama, forming Crater Lake in or Egon, USA. Differences. In conclusion, effusive volcanic eruptions are a fascinating and important part of our planet's geology. They are responsible for the formation of some of the most iconic features on Earth, such as shield volcanoes and lava plateaus. While they may not be as dramatic as explosive eruptions, they can still pose significant hazards to communities and infrastructure. However, they bring certain benefit as they fertilize soil and create new land, offering insights into harnessing natural resources for the betterment of humanity. Q169. Compare the erosional and depositional landforms formed by wind and waves. 15 marks, 250 words, core demand of question. Waves. Waves. Discuss the differences between the erosional and depositional landforms formed by wind and. Discuss the similarities between the erosional and depositional landforms formed by wind and ANS. Wind and waves, as natural agents of erosion, shape landscapes through their erosional actions, such as the hydraulic force and abrasion of waves and the lifting and transportation of particles by winds, while also depositing sediment to form landforms like beaches, dunes, spits, barrier islands, and loess deposits. There are significant differences between the erosional and depositional landforms formed by wind and wave. Differences between erosional landforms of wind and wave characteristics: wind erosional landforms, wave erosional landforms, sand dunes, yardongs, venifacts, desert pavements, sea cliffs, wave-cut platforms, sea caves, blowholes, notches, formation process, abrasion and deflation, hydraulic action. Abrasion, corrosion features steep slopes, sharp edges, wind sculpted. Surfaces: steep cliffs, caves, platforms, notches, key locations, deserts, coastal areas with sandy soils, coastal areas with strong wave activity. However, there are many similarities between the erosional and depositional landforms formed by wind and waves. Similarities between the erosional landforms formed by the wind and waves. Abrasion and scouring. Wind and waves erode surfaces. Wind-blown sand on cliffs, e.g., Delicate Arch, and waves on coastal rocks, for example, White Cliffs of Dover. Formation of ripples and dunes. Wind makes desert ripples, e.g. Sahara, waves form coastal dunes. For example, Jockey's Ridge State Park. Deflation and erosional hollows. Wind removes particles, creating blowouts, e.g. Great Victoria Desert. Waves erode coasts, forming sea caves. For example, Azure Window. Transport of sediment. Wind carries dust, e.g. Namib Desert Dunes. Waves move coastal sediment, creating beaches, e.g., outer banks and barriers. Similarities between the depositional landforms formed by the wind and waves. Sand dunes. Wind and waves both create sand dunes in deserts, e.g. Sahara's Erg Chebbi, and coastal areas. Beaches. Wind transports sand, forming beaches on windward sides of islands. Waves deposit sand along coastlines. For example, Maldives beaches. Spits. Wind moves sediment to the coast. Waves create spits through longshore drift. For example, Spurn Head in England. Barrier islands. Wind carries sand. Waves shape and arrange it into barrier islands. For example, Outer Banks, Gulf of Mexico. Wind and waves both play crucial roles in eroding rocks, transporting sediment, and shaping distinct landforms. Understanding these processes is crucial in comprehending the dynamic nature of our planet's landscapes and the role played by wind and waves in shaping them. Q170. Discuss the concept of air mass and explain its role in macroclimatic changes. 15 marks, 250 words, core demand of question. Explain the condition of the formation of air masses. Describe their role in macroclimatic changes. ANS. An air mass is a large body of air with relatively uniform temperature, humidity, and stability characteristics throughout its horizontal extent. Air masses form over extensive regions of the Earth's surface where air remains stagnant or moves slowly for an extended period, allowing it to acquire the temperature and moisture characteristics of that area. Characteristics of air masses. Temperature. Air masses are classified based on their temperature characteristics. They can be warm, tropical, cold polar, or somewhere in between Arctic or Antarctic. Warm air masses are associated with higher temperatures, while cold air masses are associated with lower temperatures. Humidity. Air masses can also vary in terms of moisture content. They can be dry continental or moist maritime. Continental air masses are usually dry because they form over land, while maritime air masses are moist because they form over water bodies. Stability. The stability of an air mass depends on its temperature and moisture content. Warm, moist air masses are typically less stable and can lead to the formation of clouds and precipitation, while cold, dry air masses are more stable and tend to inhibit cloud formation. Source regions. Air masses acquire their characteristics from source regions, which are large areas with relatively uniform surface conditions. For instance, a polar air mass forms over the polar regions, where temperatures are constantly cold. Role in macroclimatic changes. Weather patterns. When an air mass moves from its source region to another area, it can significantly influence the weather in that region. For instance, when a cold polar air mass moves southward, it can bring frigid temperatures and snowfall to areas that were previously experiencing milder conditions. Fronts. The boundaries between different air masses are called fronts. Fronts are the primary drivers of weather systems and macroclimatic changes. When warm and cold air masses meet, it can lead to the formation of clouds, precipitation, and storms. This interaction between air masses can result in dramatic shifts in temperature and weather conditions. Seasonal changes. Air masses can also influence seasonal changes in climate. For instance, the movement of a tropical air mass towards a region during the summer can lead to hot and humid conditions, while the arrival of a polar air mass in the same region during winter can bring cold and dry weather. Precipitation. Air masses influence precipitation patterns by determining the moisture content of the air. Maritime air masses tend to be moisture-laden and can contribute to heavy rainfall when they encounter topographic barriers or frontal zones. Understanding the concept of air masses is crucial for comprehending macro-climatic changes. These vast bodies of air, characterized by uniform temperature, humidity, and stability, influence weather patterns on a large scale and dictate the conditions experienced across regions and shapes the broader climate dynamics. Q171. Explore the phenomenon and types of thermal inversion, investigating the unique elements that play a role in its manifestation within the atmosphere. 10 marks, core demand of question. Discuss the types of thermal inversion. Shed light upon the unique elements that play a role in its manifestation within the atmosphere. ANS. A thermal inversion or temperature inversion refers to an unusual phenomenon in the troposphere, the atmospheric layer closest to Earth's surface, where a layer of cooler air at the ground is topped by a layer of warmer air, contrary to the typical pattern of temperature decreasing with altitude. Freezing rain serves as an example of thermal inversion. Types of thermal inversion. Vertical advection. A vertical advection or turbulence inversion arises when a tranquil air layer is situated above turbulent air. As the turbulent layer brings warm air downward and cools its upper section through a process known as vertical mixing, the tranquil air layer above gradually becomes warmer, leading to the formation of an inversion. One practical instance of this can be observed during thunderstorms. Frontal inversion. Frontal inversion occurs along the boundary between two air masses. When a warm, less dense air mass is forced to rise over a cooler, denser air mass, it can create a temperature inversion. It frequently occurs within the moderate climate region, inducing cyclonic situations that give rise to various forms of precipitation. Radiation inversion. Radiation inversion is caused by radiational cooling of the Earth's surface at night, resulting in a layer of cold air near the ground and warmer air aloft. For instance, during clear, calm winter nights, the ground loses heat rapidly through radiation, leading to a temperature inversion where the surface is colder than the air above. Subsidence inversion. Subsidence inversion is caused by sinking air. As air descends and compresses due to pressure changes, it warms, leading to a stable layer of warm air above a cooler layer. Unique elements playing a role in the manifestation of thermal inversion in the atmosphere. Prolonged winter nights. In the prolonged nighttime hours of winter, the Earth's surface experiences an extended period of cooling. As a result, the air in direct contact with the Earth's surface becomes colder during the morning, while the air above this cooler layer remains relatively warmer. This temperature contrast contributes to the development of thermal inversion. Unclouded sky. Clouds function as thermal insulators, capturing a portion of the Earth's emitted radiation and preventing it from dissipating into the upper atmosphere. In the absence of clouds, unobstructed radiational cooling occurs at the Earth's surface, facilitating a swift decrease in surface temperature and encouraging the formation of thermal inversions. Snow cover. The presence of snow on the Earth's surface chills the air in direct contact with it, while warmer air rests above. This temperature contrast contributes to the formation of thermal inversions. Mountain-valley interaction. During the night, heat radiates rapidly from mountain slopes and valleys. This disparity leads to the development of high pressure on the mountain slopes. As a result, winds flow from the mountain slopes toward the valleys, causing an upward movement of relatively warmer air from the valleys. This situation positions warm air above cold air, giving rise to a thermal inversion. Dry and calm air. Dry and calm air conditions enable the swift surface cooling and restricting vertical air mixing. This pivotal role of dry and calm air results in a pronounced temperature contrast between the Earth's surface and the upper atmosphere, fostering the development of a stable, cold air layer near the ground and, consequently, the formation of thermal inversions. Thermal inversions, driven by unique elements, exert a profound influence on weather patterns, air quality, and regional climates. To effectively anticipate and mitigate the repercussions of thermal inversions, such as air pollution, reduced visibility, and temperature anomalies, it is imperative to comprehend these factors. This understanding, in turn, will provide valuable insights into the intricacies of our atmosphere and its extensive impact on our world's future. Extra edge. Thermal inversions are known for their ability to trap pollutants near the surface. When a thermal inversion occurs, pollutants emitted from sources like vehicles and industrial facilities are unable to disperse and mix with the atmosphere. This can result in poor air quality and the accumulation of smog. This is one of the major reasons for high levels of pollution in Delhi, especially during winters. Q172. Describe the characteristics of the trade wind inversion and its effects on weather conditions in the tropics. 15 marks, core demand of question. Highlight the characteristics of trade wind inversion. Discuss the effects of trade wind inversion on the weather conditions in the tropics. ANS. A trade wind inversion, TWI, is a meteorological phenomenon characterized by a layer of warm air aloft that acts as a lid, trapping cooler air beneath it. It originates on the eastern sides of the tropical oceans and steadily increases in height and decreases in strength moving westward and equatorward. Characteristics of trade wind inversion. Temperature gradient. Trade wind inversions are marked by a distinct temperature difference between the warm air above and the cooler air below. This temperature contrast is responsible for the inversion's stability. Altitudinal variations. The height of the trade wind inversion increases as you move westward and equatorward from its origin point in the eastern parts of oceans. For example, in the North Pacific, a trade wind inversion ascends from less than 500 m at the California coast to over 2,000 m at Hawaii. Strength variability. The strength of the trade wind inversion decreases as you move westward and equatorward from its origin point in the eastern parts of oceans. Thickness of the inversion layer can vary from tens of meters to more than 1,000 meters. For example, average thickness of the inversion layer is about 400 m. Stability. The warm air layer aloft creates stable atmospheric conditions, inhibiting vertical air movement, convection, and mixing. This stability can lead to calm and clear weather in the region beneath the inversion, as seen in the tropical North Atlantic region across all seasons. Persistence. Trade wind inversions can persist for extended periods, often lasting days or even weeks, making them a prominent feature in the affected regions. Trapping of moisture and pollution. These inversions act as a barrier that can trap moisture, pollutants, and aerosols beneath them. This can lead to the formation of fog, low-level clouds, and poor air quality, especially in coastal areas. Effects of trade wind inversion on the weather conditions in the tropics. Stable atmospheric conditions and the suppression of convection. Trade wind inversions create stable atmospheric conditions. This stability inhibits the vertical movement of air, which is essential for the development of thunderstorms and other convective activity. As a result, areas under a trade wind inversion tend to experience fewer thunderstorms and less intense rainfall. For example, in the tropical North Atlantic region, TWI serves as an important stabilizing mechanism. Temperature profile. The temperature lapse rate in a trade wind inversion is inverted, meaning that temperature increases with height instead of decreasing. This leads to a noticeable temperature difference between the surface and the upper levels of the inversion layer, which significantly influences local weather conditions. For example, it is exemplified by the TWI in the Caribbean Basin. Moisture trapping. The inversion layer acts like a cap, preventing the upward movement of moist air. This can lead to the accumulation of moisture near the surface, resulting in higher humidity levels. For example, TWI found in the Hawaii region. Cloud formation and fog. The inversion often leads to the formation of low-level clouds, or fog. Moist air near the surface is trapped beneath the warm, dry air in the inversion layer. This can lead to the development of stratocumulus clouds, or fog, especially over coastal regions. Limited vertical mixing. The presence of an inversion limits the vertical mixing of air masses. This means that pollutants, such as smog or industrial emissions, can become trapped near the surface, potentially leading to poor air quality. The trade wind inversion is a distinctive meteorological phenomenon observed in the tropics. These trade wind inversions exert a strong influence on the tropical climate, contributing to both the unique weather patterns and challenges faced in these regions. Understanding these characteristics and effects is essential for meteorologists and climate scientists studying tropical meteorology. Extra edge, trade wind inversion. The temperature change as you go higher in a specific area of the trade wind zone is called a lapse rate inversion. This is particularly important in tropical weather studies. The warm, moist air from the tropics reaches about 2-3 kilometers above the ground, but is stuck there because of the dry, warm air sitting higher up. This dry air sinks down from high-pressure areas in the subtropics. This inversion happens where the descending warm air meets the cooler sea breeze. You can spot the start of this inversion where a layer of clouds begins. Fog and low-level clouds associated with the inversion can reduce visibility, particularly over coastal areas. This can affect transportation and aviation. Trade wind inversions can influence larger climate patterns, such as El Niño and La Niña events. They can either reinforce or weaken the typical climate conditions associated with these phenomena. Q173. Elaborate on the process of air mass formation while also providing a general classification of air masses. 10 marks, core demand of question. Mention the process of air mass formation. Explain the general classification of air masses. ANS. An air mass is a large volume of air defined by its temperature and water vapor content. The geographical region and the specific conditions of the region where an air mass forms influence its characteristics significantly. Understanding the formation and classification of air masses is pivotal in meteorology, offering insights into weather patterns and climatic conditions. Process of air mass formation. Source region. Air masses form in large, stable regions known as source regions. A case in point is the Arctic region where continental polar air masses develop, characterized by their cold and dry properties due to the extreme conditions prevailing in this polar region. Temperature and humidity. The specific climate of the source region molds the temperature and humidity level of an air mass. The maritime tropical air masses, which develop over the Caribbean Sea, for instance, are generally hot and carry high moisture content. Stability and duration. They acquire characteristics of their source region over an extended period. E.g., the maritime air masses influencing the South Asian monsoons stabilize over the Indian Ocean for several days, absorbing moisture before moving towards the Indian subcontinent. High-pressure systems. These systems, especially in polar and subtropical regions, facilitate the birth of air masses. The Siberian High, a high-pressure system during winter, fosters very cold and dry air masses which influence a large part of the Asian continent. Seasonal variations. Seasons play a pivotal role, like the continental air masses from Canada are distinctly colder and drier during winter, contrasting sharply with their warmer and slightly more humid nature in summer, affecting the North American weather patterns accordingly. Solar radiation. It has a direct bearing on an air mass's temperature. Equatorial regions, receiving high solar radiation all year round, give birth to warm and humid air masses, which significantly impact the tropical climate, making it hot and wet most of the year. Topography. The geographical layout of a region, including features like mountains, influence the forming air masses. E.g., the air masses developing over the Rockies are distinctively dry due to the shadow effect and vary considerably in temperature due to the changing elevations. Wind and convergence zones. Wind patterns aid air mass formation, especially in areas where different air masses converge, such as the ITCZ, where the meeting of trade winds fosters the development of warm, humid air masses, significantly influencing the tropical weather conditions. General classification of air masses. Maritime tropical. MT, they are known for their warm and humid characteristics, originating from tropical oceanic areas. E.g., the air masses generated over the Gulf of Mexico, which play a significant role in shaping the weather of southeastern regions of the USA. Continental tropical. CT, they are warm yet dry, forming over desert areas like the Sahara Desert. These masses greatly influence North African weather, rendering it extremely dry and hot. The hot and dry winds can sometimes carry desert dust over long distances. Maritime polar MP. Cold and humid. These air masses are conceived over cold ocean waters in regions like the North Atlantic. They influence Western European climates, bringing cold and moist weather patterns, and are largely responsible for the unpredictable weather in the UK. Continental polar, CP, forming over land areas in polar regions. These cold and dry air masses often originate in Siberia during the winter season. They influence the cold weather patterns in East Asia, with temperatures plunging significantly during winter. Continental Arctic, CA. These air masses, born in Arctic regions, are recognized for extremely low temperatures. Their incursion into North America, especially Canada, results in frigid conditions, dictating a harsh winter season characterized by substantially low temperatures. Understanding these classifications helps in predicting weather phenomena, aiding meteorologists in forecasting weather patterns accurately and understanding climate dynamics at various geographical locations. It forms the crux of weather prediction science, offering insights into how different regions experience diverse weather patterns. Q174. Discuss the interweaving of various factors that impact the Earth's heat budget. Analyze how alterations in the cryosphere can disrupt this delicate equilibrium, triggering potential consequences for the planet's thermal balance. 15 marks, 250 words, core demand of question. Describe the factors impacting Earth's heat budget. Highlight the alterations in the cryosphere, their impact on the Earth's heat budget, and the triggering of potential consequences for the planet's thermal balance. ANS. The Earth's heat budget refers to the balance between incoming solar radiation and outgoing terrestrial radiation that determines the overall energy balance of our planet. Several factors impact this heat budget, contributing to the complex dynamics of Earth's climate. Factors affecting the Earth's heat budget. Solar radiation. The amount of solar radiation received by the Earth varies with factors like the Earth's axial tilt and orbital variations, influencing the total energy available for heating the planet. Albedo. The reflectivity of different surfaces affects how much solar radiation is absorbed or reflected back into space. Light-colored surfaces like ice and snow have high albedo and reflect more energy, contributing to a cooling effect. In contrast, darker surfaces like oceans and forests have lower albedo and absorb more energy, leading to warming. Greenhouse gases. Greenhouse gases trap outgoing heat, maintaining Earth's warmth, but human activities intensify this effect, disrupting the heat budget by releasing more greenhouse gases through fossil fuel burning and other activities. Atmospheric composition. Aerosols, which are tiny particles suspended in the atmosphere, interact with solar radiation. Some aerosols can scatter and reflect sunlight back into space, leading to a cooling effect. For example, volcanic eruptions release aerosols, temporarily cooling the Earth's surface by reducing solar radiation. Ocean heat storage. The oceans act as a massive heat reservoir, absorbing and storing vast amounts of solar energy. Changes in ocean currents and temperatures influence how heat is distributed globally, affecting weather patterns and climate conditions. Atmospheric circulation. Atmospheric circulation redistributes heat across Earth, transferring it from the equator to the poles and from oceans to continents, influencing climate zones and regional weather patterns, thus affecting the heat budget of the planet. Land use and land cover changes. Human-induced changes in land use and land cover impact the Earth's heat budget. Deforestation reduces vegetation that can store solar energy, causing localized warming, while urbanization creates urban heat islands due to increased heat retention in concrete and asphalt. Cloud cover. Clouds play a complex role in the Earth's heat budget. They can reflect incoming solar radiation, cooling effect, and absorb and re-radiate terrestrial radiation, warming effect. The net impact depends on factors like cloud type, altitude, and thickness. Thick, low-altitude clouds trap heat, contributing to warming, while thin, high-altitude clouds may have a cooling effect. Feedback mechanisms. Changes in one component of the Earth's heat budget can trigger feedback mechanisms that amplify or dampen climate impacts. For instance, as the Arctic ice melts due to global warming, it exposes darker ocean water, increasing energy absorption and accelerating ice melt, creating a positive feedback loop that further warms the planet. Alterations in the cryosphere. Disrupting the Earth's heat budget and triggering potential consequences for the planet's thermal balance. Melting glaciers and ice sheets. Cryospheric changes increase sea level rise, disrupting the Earth's heat budget by altering ocean circulation and coastal temperatures. For example, Greenland ice sheet and Arctic glacier melting, for instance, raise sea levels, affecting coastal ecosystems and communities globally. Decline in Arctic sea ice. Arctic sea ice has decreased by 13% per decade since 1979. Reduced ice cover lowers Earth's albedo, increasing solar energy absorption, amplifying ice melting, and accelerating climate change, affecting global weather patterns. Thawing permafrost. Permafrost in the northern hemisphere is thawing at an increasing rate of about 10% per decade, releasing methane and carbon dioxide, intensifying the greenhouse effect, trapping more heat, and contributing to global warming, disrupting the Earth's heat budget. Changes in ocean salinity. Melting glaciers and ice sheets introduce freshwater, altering ocean salinity levels, which can disrupt the global ocean conveyor belt, affecting heat distribution and circulation. For example, the slowdown of the Atlantic Meridional Overturning Circulation, AMOC, could lead to shifts in climate patterns, impacting weather systems worldwide. Impact on polar ecosystems. Cryosphere alterations disrupt polar habitats, risking species extinction and ecosystem imbalances. Disrupted food chains and biodiversity loss impact the planet's thermal balance, as ecosystems regulate temperature and carbon cycling. Altered snow cover. Global snow cover has declined by about 10% since 1960. Reduced global snow cover affects the Earth's heat budget by increasing heat absorption and decreasing Earth's albedo, accelerating warming trends, and disrupting hydrological cycles. Ocean acidification. The melting of cryospheric ice releases carbon dioxide into the atmosphere, leading to increased carbon dioxide levels in the oceans and causing ocean acidification. This disrupts marine ecosystems, particularly organisms with calcium carbonate structures like corals and shellfish, leading to reduced growth and survival rates. This disruption in the marine ecosystem can have cascading effects on marine food webs and biodiversity, further exacerbating the impacts of cryospheric ice melting on the Earth's heat budget and climate. The Earth's heat budget is crucial for our planet's climate system, with far-reaching implications for life. By embracing innovation, sustainable policies, and global collaboration, we can secure a promising future, safeguard thermal equilibrium, and address climate change challenges. Extra Edge: Solutions to maintain Earth's heat budget. Geoengineering techniques. Explore and deploy geoengineering techniques, such as solar radiation management and carbon capture and storage, to actively manage the Earth's heat budget and counteract the effects of global warming. Floating reflective islands. Design and deploy floating islands covered with reflective materials in strategic locations on oceans to increase albedo, reflecting more solar radiation back into space and reducing heat absorption. Ocean-based heat pumps. Develop and implement ocean-based heat pump systems that extract heat from the ocean surface and transport it to deeper, cooler layers, effectively releasing excess heat into the deep ocean. Artificial snow albedo enhancement. Employ advanced snow-making technologies in regions with declining snow cover to increase albedo and mitigate the impact of reduced snow on the Earth's heat budget. Cloud seeding for cooling. Investigate and implement cloud seeding techniques to induce the formation of high-altitude clouds with cooling effects, helping to regulate regional and global temperatures. Climate-smart urban planning. Promote climate-smart urban planning that incorporates green infrastructure, cool roofs, and urban green spaces to mitigate the urban heat island effect and reduce local heat retention. Carbon farming and soil sequestration. Encourage carbon farming practices and soil carbon sequestration to capture atmospheric carbon dioxide and enhance soil's ability to retain heat and moisture. Smart agriculture and water management. Implement precision agriculture and efficient water management techniques to reduce agricultural emissions and optimize water usage, thus contributing to the heat budget's equilibrium. Solar radiation deflecting satellites. Research and develop space-based solar radiation deflecting satellites that can redirect a portion of solar radiation away from Earth, acting as a natural heat budget regulator. Eco-friendly transportation. Encourage the adoption of eco-friendly transportation options, such as electric vehicles and public transit, to reduce carbon emissions and contribute to a more balanced heat budget. Q175. In a nutshell, briefly describe concept of the Intertropical Convergence Zone, ITCZ. Also, explore its relation to global atmospheric circulation. 10 marks, 150 words, core demand of question. Describe the characteristics of ITCZ. Explain the relation of ITCZ to global atmospheric circulation. ANS. The ITCZ is a low-pressure belt near the equator, between 5 degrees north and 5 degrees south latitudes, where trade winds from both hemispheres converge, causing upward movement of warm, moist air, resulting in clouds, frequent rainfall, and thunderstorms. Characteristics of the Intertropical Convergence Zone, ITCZ. Convergence of trade winds. It is the convergence zone where the trade winds from the northern hemisphere and southern hemisphere meet and ascend due to the Earth's rotation and Coriolis effect. Low pressure area. The ITCZ is characterized by low atmospheric pressure, which results from the rising warm and moist air. Frequent precipitation. The convergence of moist air creates a region of abundant rainfall and thunderstorms, making it one of the wettest areas on Earth. Seasonal movement. The ITCZ shifts its position northward during the northern hemisphere's summer and southward during the southern hemisphere's summer, following the apparent movement of the sun. This seasonal movement influences the wet and dry seasons in tropical regions. Relation to the global atmospheric circulation. Hadley cell circulation. The ITCZ is part of the Hadley cell, where warm air rises near the equator, creating low pressure in the ITCZ. This air moves poleward at higher altitudes, forming high-pressure subtropical highs. Trade winds. The convergence of air in the ITCZ generates trade winds that blow from east to west in the tropics, influencing ocean currents and tropical weather patterns. Monsoons. The seasonal movement of the ITCZ leads to shifting monsoons, bringing heavy rainfall as it moves northward during northern hemisphere summer and southward during southern hemisphere summer. Rainfall distribution. The ITCZ is associated with abundant rainfall and intense convection, serving as a primary source of precipitation in the tropics and influencing global rainfall patterns. Climatic zones. The ITCZ defines distinct climatic zones, with tropical climates near the equator experiencing high temperatures and high precipitation. Its movement affects the boundary between tropical and subtropical regions, impacting climate and vegetation patterns. The ITC is an integral part of the global atmospheric circulation, specifically the Hadley cell. It influences the movement of air masses, formation of trade winds, and distribution of rainfall on a global scale. ITCZ and global atmospheric circulation together contribute to the weather patterns, climate variations, and ecosystem dynamics in different parts of the world. Q176. Briefly delineate the phenomenon of triple dip La Nina. Also explain the causal factors linked to it, subsequently, mentioning the impact it has on global weather pattern. 10 marks, 150 words, core demand of question. Mention the causes of triple dip La Nina phenomenon. Enumerate the impacts of the triple dip La Nina phenomenon on global weather patterns. ANS. The term triple dip La Nina phenomenon refers to a series of 3 consecutive La Nina events that occur in the tropical Pacific Ocean. La Nina is a climate pattern characterized by cooler than normal sea surface temperatures in the central and eastern equatorial Pacific Ocean. Causes of the triple dip La Nina phenomenon. Oceanic and atmospheric interactions. It is primarily caused by interactions between the ocean and the atmosphere, specifically the coupling between the oceanic and atmospheric circulations. Cool surface temperatures. As a result of enhanced upwelling, the sea surface temperatures in the eastern and central equatorial Pacific become cooler than average during a La Nina event. It acts as a fodder for subsequent La Nina. Double dip La Nina factor. In the triple dip La Nina phenomenon, after the initial La Nina event and the subsequent recharge phase, another La Nina event occurs before the oceanic conditions fully recover. Delayed atmospheric response. The atmospheric response to the first La Nina event may not dissipate quickly, leading to a delayed return to normal conditions and a higher likelihood of subsequent La Nina events. Ocean circulation. The strengthening of trade winds enhances the Walker circulation, a large-scale atmospheric circulation pattern that involves rising air over the western Pacific and descending air over the eastern Pacific. This reinforces the cooling of sea surface temperatures in the east and leading to triple La Nina. Positive feedback loop. The cooler sea surface temperatures during La Nina reinforce the atmospheric circulation patterns, leading to a positive feedback loop that can sustain or amplify subsequent La Nina events. Impacts of the triple dip La Nina phenomenon on global weather patterns. Shifted rainfall patterns. For instance, it may result in increased rainfall in regions such as India, Australia, causing flooding and disrupting agricultural activities. Drought conditions. This was observed during the 2010-2012 triple dip La Nina event, which contributed to severe droughts in the southwestern United States, reducing water supplies and impacting ecosystems. Spread of vector-borne diseases. Stagnant water and increased humidity due to heavy rainfall provide favorable conditions for the breeding of disease-carrying mosquitoes, leading to an increase in diseases like malaria and dengue in India. Disrupted fishing activities. Cooler sea surface temperatures impact marine ecosystems, leading to a decline in fish populations in the Indian Ocean. Increased frequency of extreme weather events. Triple-dip La Nina can lead to an increase in extreme weather events like cyclones, floods, and heavy rainfall in some regions of India. Impact on monsoon systems. For instance, in Southeast Asia, it can lead to drier conditions due to relatively cool water in the equatorial eastern Pacific. Such droughts affect agriculture and water resources. Conversely, increased rainfall and flooding can occur in the western Pacific region. Implications for global climate change. Understanding the impacts of triple-dip La Nina is crucial for comprehending the interactions between natural climate variability and anthropogenic climate change. The potential impacts of the triple-dip La Nina phenomenon on global weather patterns can affect different regions differently. It's important to note that the specific effects can vary depending on the intensity and duration of the events, as well as the regional characteristics. Q177. How do ocean currents influence the worldwide distribution of marine resources? 10 marks, core demand of question. Discuss how ocean currents influence the worldwide distribution of marine resources. Substantiate your points with relevant examples. ANS. An ocean current is a continuous, directed movement of seawater in the ocean, driven by various forces such as wind, temperature, salinity, and the Earth's rotation. Examples of ocean currents include the Peruvian Current, Labrador Current, and Falkland Current. These currents play a crucial role in concentrating and dispersing various marine resources, valuable materials and assets derived from the world's oceans and seas, leading to the differential distribution of marine resources worldwide. Influence of ocean currents on the worldwide distribution of marine resources. Fisheries. Ocean currents play a pivotal role in the distribution of essential nutrients, plankton, and fish larvae, impacting the global presence of fish populations. For example, the convergence of the Labrador and Gulf Stream currents has created one of the richest fishing grounds in the North Atlantic Ocean. Mineral resources. Ocean currents are instrumental in dispersing or concentrating mineral deposits on the seafloor, shaping mineral resource availability. For example, the Clarion-Clipperton Zone in the Pacific Ocean, known for vast polymetallic nodule formations. Marine biodiversity. Ocean currents serve as dynamic conveyor belts that bring together diverse marine species from different regions, creating biodiversity hotspots. They also facilitate the dispersion of marine organisms, influencing the composition of ecosystems. For example, notably, the Gulf Stream in the North Atlantic creates prime conditions for phytoplankton and zooplankton growth, influencing the distribution of species like Atlantic mackerel and bluefin tuna. Coral reefs. Ocean currents play a pivotal role in shaping the geographic boundaries of reef formation by delivering vital nutrients and maintaining the interconnectedness of reef populations through the dispersal of coral larvae and other marine organisms. For example, the East Australian Current, which has significantly contributed to the extensive formation of the Great Barrier Reef in the Pacific Ocean off northeastern Australia. Marine biotechnology. Ocean currents can carry valuable microorganisms and genetic material used in marine biotechnology, such as pharmaceuticals, cosmetics, and bioplastics. For example, the Kuroshio Current in the Western Pacific transports diverse genetic material, making it an area of interest for biotechnological research. Oil and gas. Ocean currents influence the movement and dispersion of oil and gas deposits beneath the seabed. They can create eddies and gyres that affect the accumulation and distribution of hydrocarbons. For example, the Gulf Stream in the North Atlantic has played a significant role in the distribution of oil reserves along the coast of the United States. Renewable energy resources. Ocean currents are pivotal in determining the availability and strength of renewable energy sources like tidal and ocean current energy. For example, areas with robust and consistent currents, such as the Pentland Firth in Scotland or the Gulf of Maine in the United States, are ideal for deploying renewable energy technologies like underwater turbines. Ocean currents, driven by various natural forces, shape the distribution of valuable marine assets in several ways. Recognizing their profound influence is essential for preserving and responsibly managing these invaluable marine resources on a global scale, ensuring both ecological balance and sustainable utilization as we explore and harness the riches of our oceans. Q178. How does the age of oceanic crust change as one moves away from a mid-ocean ridge? And what does this reveal about seafloor spreading? 10M Core Demand of Question. Discuss how the age of oceanic crust changes as one moves away from a mid-ocean ridge. Shed light upon its revelations about seafloor spreading. ANS. The mid-ocean ridge stands as Earth's most expansive mountain range along the divergent plate boundaries, spanning almost 65,000 kilometers in length, with over 90% of it submerged beneath the deep ocean. Among the globally recognized mid-ocean ridges, the Mid-Atlantic Ridge and the East Pacific Rise are particularly well researched. This vast mountain range unlocks insights into the age progression of oceanic crust as it distances itself from mid-ocean ridges, as discussed below. Changes in the age of oceanic crust as one moves away from the mid-oceanic ridge. Younger near the mid-ocean ridge. Oceanic crust is formed at mid-ocean ridges through volcanic activity, where magma rises and solidifies. As new crust forms at these ridges, it is initially very young, often only a few million years old. This young crust is characterized by high heat flow and is relatively thin. Progressively older away from the ridge. As the oceanic crust moves away from the mid-ocean ridge, it ages. This happens because the newly formed crust at the ridge is constantly pushing the older crust away. Therefore, the farther you move from the ridge, the older the oceanic crust becomes. Increasing age, thickness, and depth. Older oceanic crust is not only older in terms of its formation, but also thicker and found at greater depths. This is because it has had more time to cool and thicken over the course of millions of years. It is also characterized by lower heat flow compared to the younger crust near the ridge. Revelations about the seafloor spreading. Confirmation of seafloor spreading. The increase in crustal age with distance from the mid-ocean ridge provides strong evidence for the concept of seafloor spreading. Seafloor spreading is the process by which new oceanic crust is formed at mid-ocean ridges and then moves away from the ridge over time. The older crust found farther from the ridge corroborates the idea that new crust is continuously created at the ridge axis. Symmetric patterns. The age-depth relationship on both sides of a mid-ocean ridge is often symmetric. This means that if you measure the age of oceanic crust on one side of the ridge and then cross to the other side, you will find a similar pattern of increasing age as you move away from the ridge. This symmetry supports the notion that the new crust is created at the ridge and spreads outward in opposite directions. Quantifying plate movement. By studying the age of oceanic crust, scientists can estimate the rate at which tectonic plates are moving apart. Knowing the rate of seafloor spreading helps in understanding the dynamics of plate tectonics and the geological processes that shape Earth's surface. Rejuvenation of the ocean basins. Younger oceanic crust near mid-ocean ridges is typically characterized by higher heat flow, active volcanism, and shallower depths, while older crust farther from the ridge is cooler, thicker, and found at greater depths. These differences in crustal characteristics, along with age, provide insights into the history and evolution of ocean basins, demonstrating how they have expanded over time due to seafloor spreading. The transition of oceanic crust away from a mid-ocean ridge marks a significant transformation, demonstrating the dynamic forces at play in Earth's crust and forming a cornerstone in our comprehension of seafloor spreading. While our current understanding has constraints, especially in dating older oceanic crust, future advances in geological research and technology offer promise in delving deeper into this process and broadening our comprehension of Earth's geological dynamics. Extra edge. Due to the connection between age and the likelihood of subduction, there is a scarcity of oceanic crust exceeding 125 million years in age, and virtually none surpassing the 200 million year mark. Consequently, using seafloor dating as a tool for investigating plate movements beyond the Cretaceous period becomes less practical. In such cases, geologists turn to dating and examining continental crust for a more reliable approach. Q179. Tsunamis are often referred to as silent killers. Discuss the triggers behind the formation of tsunamis and their devastating impact on coastal regions. 15M Core Demand of Question. Shed light on the triggers behind the formation of tsunamis. Discuss their devastating impact on the coastal regions. ANS. Tsunami referred to as catastrophic ocean wave, usually caused by a submarine earthquake, an underwater or coastal landslide, or a volcanic eruption. In deep water, a tsunami can travel as fast as 800 kilometers, 500 miles per hour. The wavelengths are enormous, sometimes exceeding 500 kilometers, about 310 miles. But the wave amplitudes, heights, are very small, only about 30 to 60 centimeters, 1 to 2 feet. An illustrative instance is the devastating 2004 Indian Ocean tsunami, which resulted in the loss of hundreds of thousands of lives and widespread destruction. They approach coastlines with little or no warning signs, making them highly dangerous and deadly, hence often referred to as silent killers. Triggers behind the formation of tsunamis. Earthquakes. Tsunamis are often triggered by underwater earthquakes. These seismic events can cause the seafloor to uplift or subside abruptly, displacing a large volume of water. For example, the 2011 Tohoku earthquake in Japan generated a massive tsunami that reached heights of up to 133 feet, 40.5 meters. Landslides. Submarine landslides, especially in coastal or underwater terrains, can displace substantial amounts of water and generate tsunamis. For example, 1958 Lituya Bay landslide in Alaska, which created a tsunami that reached a height of approximately 1,720 feet, 524 meters. The tallest tsunami wave in recorded history. Volcanic eruptions. Explosive volcanic eruptions occurring near or beneath the ocean can also induce tsunamis. When volcanic material, like ash and rock, plunges into the water, it displaces it, causing waves. For example, the eruption of Krakatoa in 1883 generated a tsunami that killed tens of thousands of people across coastal regions in Indonesia. Faulting. Seafloor faulting can result in sudden vertical displacement of the seabed, displacing seawater and initiating a tsunami. For example, the underwater Samarkand fault off the eastern coast of Japan caused the 1933 Samarkand tsunami, which reached heights of up to 94 feet, 28.7 meters. Upliftment of the oceanic bottom. In some cases, geological processes, such as the rapid upliftment of the oceanic bottom due to tectonic forces, can trigger tsunamis. For example, 1946 tsunami in the Aleutian Islands, Alaska, caused by the upliftment of the seafloor. Plate tectonics. Interactions between tectonic plates can create zones of subduction or collision, leading to powerful earthquakes and tsunamis, for example. The subduction of the Indian plate beneath the Burma plate led to the devastating 2004 Indian Ocean tsunami. Anthropogenic activities. Human activities, such as underwater nuclear tests or large-scale coastal engineering projects, have the potential to trigger tsunamis. Devastating impact of tsunamis on the coastal regions. Loss of life and injury. Tsunamis can cause massive casualties as they inundate coastal areas with a wall of water, sweeping away people and causing severe injuries. For example, the 2004 Indian Ocean tsunami resulted in the tragic loss of about 230,000 lives across multiple countries, leaving countless others injured and traumatized. Displacement and homelessness. Tsunamis can force people to flee their homes, leading to temporary or long-term displacement and homelessness. Economic impact. Coastal regions often rely on industries such as fishing and tourism, which can be severely impacted by tsunamis, leading to economic downturns. For example, worldwide, since the beginning of the 21st century, 48 tsunamis have resulted in approximately $300 billion worth of economic losses. Destruction of infrastructure. Tsunamis can destroy buildings, roads, bridges, and other critical infrastructure, disrupting the functioning of coastal communities, for example. The 2011 Fukushima nuclear accident due to Tohoku earthquake and tsunami. It resulted in grid failure and damaged nearly all of the power plant's backup energy sources. Environmental damage. Tsunamis can have long-lasting ecological impacts, such as damage to coastal ecosystems, contamination from debris and pollutants, and destruction of coral reefs. For example, in the aftermath of the 2004 tsunami in Indonesia, Bappena's State Ministry of National Development Planning estimated that 20% of seagrass beds, 30% of coral reefs, 25–35% of wetlands, and 50% of sandy beaches along the west coast were damaged. Radiation hazard. Tsunamis can pose a radiation hazard when they damage nuclear power plants, potentially leading to radioactive leaks and contamination. For example, in March 2011, the Tohoku tsunami in Japan damaged the Fukushima Daiichi nuclear power plant, resulting in the release of radioactive materials into the environment. To conclude, tsunamis, aptly referred to as silent killers, are a formidable force of nature capable of causing widespread devastation in coastal regions. As we confront the reality that globally, more than 700 million people live in low-lying coastal areas and small island developing states, residing in vulnerable coastal areas, it is imperative that we continue to invest in preparedness, early warning systems, and sustainable coastal development to mitigate the potentially catastrophic effects of future tsunamis. Extra edge. While rare, the impact of a large meteorite or asteroid in an ocean can produce a tsunami. Although no recorded instances of this have occurred in human history, computer simulations suggest the potential for tsunami formation in such scenarios. About 80% of the tsunamis happen within the Pacific Ocean's Ring of Fire. Ring of Fire is a geologically active area where tectonic shifts make volcanoes and earthquakes common. Survivors of tsunamis often suffer from psychological trauma, including post-traumatic stress disorder, PTSD, which can have lasting effects on mental health. Q180. Examine the intricate interplay between physical processes and climatic factors influencing the genesis and dissipation of oceanic eddies, while assessing their profound effects on marine ecosystems and global climate patterns. 15M Core Demand of Question. Explain how interplay between physical processes and climatic factors influences the genesis of oceanic eddies. Explain how interplay between physical processes and climatic factors influences the dissipation of oceanic eddies. Suggest the profound effects of oceanic eddies on marine ecosystems and global climate patterns. ANS. Oceanic eddies are like underwater tornadoes. They swirl around and can move warm or cold water across the ocean. For example, eddies in the Gulf Stream help carry warm water from the tropics up towards the North Atlantic. They're important for ocean health and climate. Interplay between physical processes and climatic factors influences the genesis of oceanic eddies. Ocean currents. Strong ocean currents, like the Gulf Stream, can create eddies when the flow of water gets disturbed. It's similar to the swirls you see when a fast-moving river hits a big rock. Wind. Wind blowing over the ocean surface can stir the water, creating ripples that can grow into bigger eddies. Like when winds from a storm blow over the ocean, they can help form eddies. Water density differences. Eddies can also form when water of different temperatures or salinity, saltiness meet. Imagine pouring syrup into water. It doesn't mix well and creates swirls. That's like an eddy. Tides. The regular push and pull of the ocean's tides can generate eddies. Just as tide changes can cause ripples in a bay or estuary, they can also create larger-scale eddies in the open ocean. El Niño or La Niña. These climate patterns change wind and ocean current patterns. These shifts can lead to more or less eddy formation, depending on the conditions. Ocean fronts. These are boundaries where different bodies of water meet, like warm water meeting cold water. This clash can create instabilities that lead to the formation of eddies. Atmospheric pressure changes. Large-scale changes in atmospheric pressure, such as those caused by moving weather systems, can cause changes in sea surface height, leading to eddy formation. Interplay between physical processes and climatic factors influences the dissipation of oceanic eddies. Friction with seabed. When an eddy encounters shallow waters or an uneven ocean floor, it can slow down due to friction. This process gradually reduces the energy of the eddy, leading to its dissipation. Encountering coastlines. If an eddy moves towards a coast, the coastline can disrupt its circular motion, leading to its eventual disintegration. For instance, eddies in the Gulf Stream often dissipate when they hit the eastern coast of North America. Merging with other eddies. Sometimes, when two eddies come close, they can merge into one larger eddy. While this new eddy might be bigger, the overall energy is conserved, leading to the original eddy's dissipation. Heat exchange. Eddies can lose energy through heat exchange with the atmosphere, which can lead to their dissipation. In colder regions, this heat loss can be significant and cause the eddy to break down faster. Wind stress. Strong winds can either aid in eddy formation or contribute to their decay. If winds blow in a direction opposite to the eddy's spin, they can disrupt its motion and contribute to its dissipation. Sea surface temperature. Changes in sea surface temperature, often influenced by seasons or larger climate processes, can impact the stability of eddies and influence their dissipation. Changes in water density. Just as differences in water density can create eddies, changes in these differences, due to warming or cooling, for instance, can destabilize and help dissipate them. Profound effects of oceanic eddies on marine ecosystems and global climate patterns. Nutrient distribution. Oceanic eddies can churn up nutrients from the ocean's depths and spread them around. This is like giving the ocean a big stir, helping feed small plants and animals living in the water. Marine food chain. By bringing up these nutrients, eddies help boost the growth of tiny plants called phytoplankton, the base of the ocean's food chain. This can lead to more fish and other sea creatures in those areas. Heat transport. Eddies help move heat around in the ocean. To exemplify, eddies formed in the Gulf Stream transport warm water and heat from the tropics towards the colder North Atlantic, influencing the region's climate. Carbon storage. The ocean absorbs a lot of the Earth's carbon dioxide, CO2, a greenhouse gas. Eddies can carry this CO2 deep into the ocean, storing it away from the atmosphere and helping to combat climate change. Oxygen supply. When eddies stir up the water, they also bring oxygen down into the deeper ocean. This is crucial for the survival of marine creatures living at depth. Climate buffer. By moving heat and CO2 around, eddies help the ocean act as a buffer against rapid climate change. Without them, Earth's climate could change much more quickly. Marine migration. Some marine animals, like turtles and seals, use eddies as rest stops during long migrations. They're like underwater pit stops, providing a bounty of food for the journey. Going ahead, given the complexity and global scale of these processes, the study of oceanic eddies is of paramount importance for improving our understanding and prediction of climate change and its impacts on marine ecosystems. Q181. In what ways are cyclones and anticyclones similar, and how do they differ? 10M Core Demand of Question. Discuss the ways in which cyclones and anticyclones are similar. Shed light upon the differences between cyclones and anticyclones. ANS. Cyclones and anticyclones are the two primary atmospheric systems where a cyclone, exemplified by Hurricane Katrina, involves the rapid inward circulation of air masses around a low-pressure center. Conversely, an anticyclone, like the Azores High, features the swift outward circulation of air masses around a high-pressure center, exhibiting rotational patterns opposite to cyclones. Ways in which cyclones and anticyclones are similar. Atmospheric systems. Both cyclones and anticyclones are large-scale atmospheric systems that influence weather patterns in the regions where they are present. Formation. Both systems form due to various meteorological factors, including temperature differences, pressure gradient, humidity levels, and the Earth's rotation. For example, cyclones can develop when warm, moist air rises and creates a pressure gradient, while anticyclones may form when cool, dry air descends, creating another pressure gradient. Air circulation. They both involve the movement and circulation of air masses. For example, cyclones are characterized by inward and upward air circulation, while anticyclones exhibit downward and outward air circulation. Rotation. Both cyclones and anticyclones exhibit rotation, with air moving around a central point. For example, to illustrate, cyclones rotate around low-pressure centers, while anticyclones revolve around high-pressure centers. Coriolis force. The rotation direction of both systems is influenced by the Coriolis effect. For example, the Coriolis force causes cyclones and anticyclones in the northern hemisphere to rotate counterclockwise and clockwise, respectively, while in the southern hemisphere, their rotation directions are reversed. Influence on weather. They can both have significant impacts on local weather and climate. For example, Cyclone Amphan caused heavy rainfall in regions including East Midnapore, North and South 24 Parganas, Howrah, Hooghly, and West Midnapore, whereas a polar anticyclone usually creates cool and dry weather in Canada, the USA, and northern Eurasia. Differences between cyclones and anticyclones. Characteristic cyclone-anticyclone atmospheric pressure low-pressure system. Pressure increases on moving away from the center. High-pressure system. Pressure decreases on moving away from the center. Air circulation inward and upward, downward and outward rotation direction counterclockwise in northern hemisphere, and clockwise in southern hemisphere, clockwise in northern hemisphere, and counterclockwise in southern hemisphere, weather conditions stormy, cloudy, rainy, strong winds, exemplified by hurricanes. Calm, clear skies, stable weather, exemplified by the Azores high. Damage can cause great damage to lives and property. For example, Cyclone Tauktae resulted in at least 174 fatalities, with over 80 individuals still missing, and caused estimated losses of $1.57 billion. Does not cause loss to lives and property. Instead, it leads to pleasant weather. For example, the Bermuda Azores high brings fair weather. Global distribution found in various regions worldwide, including tropical and temperate zones, exemplified by their occurrences in the Atlantic Ocean and Pacific Ocean. Also found in different regions, but more prevalent in subtropical and high-latitude areas. For example, the Siberian high in Eurasia. The understanding of both the similarities and distinctions between these two atmospheric systems is crucial for predicting and responding to weather events and preparing for the diverse impacts these atmospheric phenomena have on our daily lives. Q182. Delve into the meteorological conditions associated with extratropical cyclones while elaborating on their distinctive characteristics. 15M Core Demand of Question. Enumerate the meteorological conditions associated with extratropical cyclones. Mention the distinctive characteristics of extratropical cyclones. ANS. Extratropical cyclones, often referred to as mid-latitude or frontal cyclones, are a prevalent weather phenomenon occurring mainly in the middle and high latitudes. Forming outside the tropical zones, these cyclones are significant weather systems with vast influences on the climate and weather patterns of the regions they affect. Meteorological conditions associated with extratropical cyclones. Temperature contrast. They prominently occur where there is a significant temperature contrast, generally where polar and tropical air masses converge. For example, in the North Atlantic region, the sharp temperature gradients leading to the nor'easters in the northeastern U.S. Frontogenesis. Frontogenesis, a process defining the birth or strengthening of a weather front, plays a pivotal role. For example, during the 1993 storm of the century, in the U.S., frontogenesis was witnessed with a rapid intensification of fronts, bringing about severe snowfalls. Jet streams. These cyclones often form and intensify near the jet streams, characterized by fast-flowing narrow air currents. For example, the European windstorm Kirill in 2007, fueled by the jet streams, showcased how these atmospheric rivers can enhance a cyclone's development. Cold and warm fronts. The dynamic interaction between cold and warm fronts leads to the formation of occluded fronts as the cyclone matures. For example, during the historic Ash Wednesday storm of 1962, which witnessed the merging of such fronts, resulting in extreme weather conditions. Wind patterns. As these cyclones develop, they induce specific wind patterns with winds spiraling inward and converging at the center, for example. The Great Appalachian Storm of 1950 in the U.S. showcased this wind pattern, with severe winds wreaking havoc over a large geographical expanse. Rossby waves. Rossby waves, large waves in the jet stream, significantly influence the life cycle of extratropical cyclones. For example, during the North Atlantic Oscillation (NAO) events, Rossby waves play a crucial role in determining the cyclone's pathway and intensity. Distinctive characteristics of extratropical cyclones. Broad spatial extent. These cyclones have a substantial spatial presence, often overshadowing their tropical counterparts. For example, the Great Storm of 1987 affected a vast area across the UK and France, showcasing the extensive geographical reach of extratropical cyclones. The spatial extent of extratropical cyclones ranges from 500 kilometers to 2,500 kilometers. Seasonal variability. The winter of 2013-14 in North America saw a spate of extratropical cyclones, highlighting the seasonal predisposition of these weather events, significantly impacting regions with massive snowfalls and cold waves. Asymmetric structure. They frequently display an asymmetric structure, having divergent meteorological dynamics on different sides. For example, the 1993 superstorm in the U.S., where one side experienced heavy snowfall while the other side encountered severe thunderstorms. Variable precipitation patterns. They exhibit a diversity in precipitation patterns, encompassing rain, snow, or mixed phases. For example, the North American blizzard of 2009 showcased varying precipitation patterns, including a mix of heavy snowfall and rain across different regions. Complex life cycle. It is intricate, passing through stages from inception to occlusion. For example, the series of cyclones impacting the UK in winter 2013-14 witnessed complex life cycles, evolving through various stages, showcasing the complexity in the developmental phases of these cyclones. Impact on weather. They substantially affect weather patterns, inducing sudden and drastic alterations in weather conditions over expansive areas. For example, the derecho of 2020, USA, brought about significant weather alterations, highlighting the transformative impact of these cyclones. Extratropical cyclones are dynamic weather systems which play a pivotal role in shaping the weather and climate of mid- and high-latitude regions. Understanding the meteorological conditions and distinctive characteristics of these cyclones is vital in weather forecasting and climate studies to mitigate their impacts effectively. Q183. Embark on a profound exploration of the phenomenon of seafloor spreading, delving into the entangled web of different forces that fuel this geological marvel and underscore its paramount significance in shaping the dynamic processes of our planet. 15 marks, 250 words, core demand of question. Discuss the forces that fuel the process of seafloor spreading. Highlight the importance of seafloor spreading in shaping the dynamic processes of our planet. ANS. Seafloor spreading is a fundamental mechanism of plate tectonics that plays a vital role in shaping the Earth's surface and redistributing heat and chemicals in the oceans. It is a geological process that occurs at mid-ocean ridges, where plates move apart, creating new oceanic crust from upwelling magma. This process shapes the Earth's surface and expands ocean basins. Forces behind the seafloor spreading. Mantle convection. Heat generated within the Earth's mantle causes convection currents, where hot, less dense material rises while cooler, denser material sinks. These convection currents cause the movement of tectonic plates, including the divergence of plates at mid-ocean ridges. Ridge push. As new oceanic crust forms at mid-ocean ridges, it pushes the adjacent plates away from the ridge due to the gravitational force. Slab pull. At subduction zones, where one tectonic plate is forced beneath another, a process called subduction occurs. The descending plate becomes cooler and denser, leading to a slab pull force that pulls the rest of the plate along with it, contributing to plate motion and seafloor spreading. Gravity. The higher elevation of mid-ocean ridges compared to the surrounding oceanic crust creates a gravitational force that drives the movement of plates away from the ridge. Tensional stresses. As the plates move apart at mid-ocean ridges, tensional stresses build up in the lithosphere. These stresses lead to fracturing and faulting, allowing magma to rise from the mantle and solidify to form new oceanic crust, which further contributes to the seafloor spreading. Basal drag. The asthenosphere, a semi-fluid layer beneath the lithosphere, exerts a basal drag force on the overlying plates. This force helps facilitate their movement over the ductile asthenosphere. Transform faults. Transform faults, which are perpendicular to mid-ocean ridges, also contribute to seafloor spreading. The sliding of plates along these faults allows for lateral movement and the transfer of motion between different segments of mid-ocean ridges. Significance of the seafloor spreading in shaping the dynamic processes of our planet. Plate tectonics. Seafloor spreading is a fundamental mechanism of plate tectonics, explaining how tectonic plates move and interact with each other. It is a driving force behind the movement of continents, influencing the arrangement of land masses and ocean basins. Ocean basin formation. Seafloor spreading is responsible for the continuous creation of new oceanic crust at mid-ocean ridges. As the plates move apart, magma upwells and solidifies, widening ocean basins and shaping the Earth's ocean floor. Geologic features. Seafloor spreading leads to the formation of distinctive geologic features, such as mid-ocean ridges, abyssal plains, and deep-sea trenches. These features have a significant impact on the distribution of underwater mountain ranges, volcanic activity, and seismic activity. Heat and chemical redistribution. Seafloor spreading plays a crucial role in redistributing heat and chemicals in the oceans. As new oceanic crust is formed and cools, it releases heat into the surrounding seawater. The process also allows seawater to infiltrate the crust, interacting with minerals and rocks and picking up various dissolved chemicals and elements. Earth's magnetic history. Magnetic striping along mid-ocean ridges provides vital clues about the history of the Earth's magnetic field. As magma cools and solidifies, magnetic minerals align with the prevailing magnetic field at that time. This phenomenon has been instrumental in confirming the concept of seafloor spreading and supporting the theory of plate tectonics. Geohazard prediction. Seafloor spreading contributes to the formation of geohazards, such as underwater earthquakes and volcanic eruptions. Understanding these dynamic processes is essential for predicting and mitigating potential risks to coastal regions and human populations. In conclusion, seafloor spreading is a pivotal process that shapes the Earth's lithosphere and influences various geological phenomena, contributing to the continuous evolution of our planet and holding potential for future discoveries in understanding our planet's dynamic processes. Q184. Explain the multifaceted forces governing the genesis of ocean currents, and expound upon their instrumental role in sculpting the enigmatic underwater geologic features. 10 marks, 150. Words, core demand of question. Discuss the various factors governing the genesis of ocean currents. Elaborate on the instrumental role of ocean currents in sculpting underwater geologic features. ANS. Ocean currents are large-scale, persistent, and directed movements of seawater that flow through the Earth's oceans, influencing the global distribution of heat, nutrients, and marine life. For example, the North Atlantic Drift, an extension of the Gulf Stream, transports warm water from the Gulf of Mexico to the eastern coast of North America and Europe, impacting climate and marine ecosystems. Factors governing the genesis of ocean currents. Gravity. Gravity generates ocean currents by creating pressure gradients that cause water to flow from regions of higher pressure to lower pressure. For example, the Antarctic circumpolar current is driven by the pressure gradient resulting from the difference in sea level between the Atlantic, Indian, and Pacific Oceans. Density differences. Density differences in water, resulting from variations in temperature and salinity, influence the genesis of ocean currents. Cold and dense water sinks, while warm and less dense water rises. For example, upwelling along western coasts, like off the coast of Peru, is driven by the upsurge of cold, nutrient-rich waters due to the convergence of surface currents and the presence of the Humboldt Current. Factors associated with the motion of Earth. Due to the Earth's west to east rotation, ocean currents near the equator flow in an east to west direction, as water lags behind its movement. Coriolis force. The Coriolis force influences ocean currents to turn to the right in the northern hemisphere and to the left in the southern hemisphere, leading to the formation of the North Atlantic Gyre and South Pacific Gyre, which are extensive circular ocean currents encompassing vast areas of these ocean basins. Ekman's spiral. Ekman's spiral generates ocean currents through wind-induced water movement, creating a downward spiral with each layer of water moving at an angle, resulting in net water transport at a 90-degree angle to the wind direction. Solar energy. When water is heated, it expands. This expansion causes the water to become less dense, which in turn creates a difference in pressure. The pressure difference drives currents. For example, sun-heated surface water in the Gulf of Mexico expands, becomes less dense, rises, and generates a pressure difference. This drives trade winds, propelling the Gulf Stream. Wind. The sun heats the Earth's surface unevenly, which creates pressure differences that drive winds. These winds blow across the surface of the ocean, causing the water to move as exemplified by the Gulf Stream, driven by trade winds. Temperature. Warm water is less dense than cold water, so it rises to the surface. This creates a difference in pressure that drives currents. For example, the North Atlantic Drift originates because of the difference in temperature between the warm water in the Gulf Stream and the cold water in the North Atlantic Ocean. Salinity. Salter water is denser than less salty water, so it sinks. This creates a difference in pressure that drives currents. For example, the water in the Mediterranean Sea is denser than the water in the Atlantic Ocean, so it sinks and flows into the Atlantic Ocean, Mediterranean outflow. Role of oceanic currents in sculpting the underwater geologic features. Canyons. Strong ocean currents erode coastlines and shape underwater canyons. For example, the Monterey Canyon off the coast of California is a deep submarine canyon formed by the erosive action of the California Current. Submarine deltas and fans. Ocean currents transport and deposit sediments, leading to the formation of submarine deltas and fans. For example, These have contributed to the formation of the Nile cone, Nile submarine fan, through the transportation and deposition of sediments carried by the Nile River. Submarine landslides. Ocean currents can trigger submarine landslides by destabilizing sediments. The Storegga slide off the coast of Norway is an example of a massive submarine landslide that resulted from the interaction of ocean currents with the seafloor. Formation of seamounts. Ocean currents can shape underwater volcanoes into seamounts. For example, the Hawaiian Islands, which were formed by volcanic activity, are an example of seamounts that have emerged above sea level due to the interaction of currents with volcanic islands. Volcanic ridge formation. Ocean currents transport volcanic materials, creating volcanic ridges and chains. For example, the Mid-Atlantic Ridge, the longest mountain range on Earth, is formed by volcanic activity and the spreading of ocean crust due to currents. Submarine canyons. Ocean currents play a role in shaping submarine canyons by scouring the seafloor. For example, the Zemchug Canyon in the Bering Sea is an example of a deep canyon formed by ocean currents. Coral reefs. Ocean currents transport larvae and nutrients to support coral growth and the formation of coral reefs, as exemplified by the Great Barrier Reef in Australia, is sustained by East Australian Current that originates near the equator and carries warm, nutrient-rich waters southward. Ocean currents, dynamic and multifaceted, intricately shape Earth's oceans, playing a crucial role in seafloor processes, including eroding coastlines, shaping canyons, transporting sediments, and forming volcanic ridges. Ongoing research and observation offer opportunities to unravel oceanic mysteries and deepen our appreciation of currents' essential role in shaping diverse underwater landscapes. Q185. Elucidate the phenomenon of internal waves prevalent in the ocean and elaborate on their instrumental role in inducing vertical mixing and facilitating the process of nutrient transport within the marine environment. 10 marks, 150 words, core demand of question. Explain the key features of internal waves and substantiate with examples. Elaborate on the instrumental role of internal waves in inducing vertical mixing. Delve into the facilitation of nutrient transport by internal waves. ANS. Internal waves in the ocean are waves that propagate within the water column, beneath the surface, as opposed to surface waves that are visible on the ocean's surface. These waves occur due to the interaction of water masses with different densities or temperature gradients. Internal waves are widespread and occur in various oceanic regions, including the North Atlantic, Mediterranean Sea, Red Sea, and more. Key features of the internal waves. Subsurface propagation. Internal waves propagate within the water column, beneath the ocean's surface, and are not visible on the water's top layer. For example, in the Strait of Gibraltar, internal waves can be observed propagating beneath the surface layer. Hidden nature. Internal waves are often invisible to the naked eye, making it challenging to detect them without specialized equipment. For example, in the Arctic Ocean, where sea ice covers much of the surface, internal waves can remain unnoticed. Generating factors. Internal waves are formed due to the interaction of water masses with different densities or temperature gradients. For example, in the equatorial Pacific Ocean, where warm surface waters meet cooler subsurface waters, internal waves are generated at the thermocline. Long wavelengths. Internal waves can have long wavelengths, ranging from a few meters to several kilometers, for example. The internal waves in the South China Sea can have wavelengths of up to 15 kilometers. High energy. Internal waves carry significant energy, leading to vertical displacements of water layers. For example, in the Bay of Fundy, Canada, tidal-driven internal waves can reach heights of over 30 meters. Role of internal waves in the induction of vertical mixing. Breaking of internal waves. When internal waves break, they can induce vertical mixing by transferring momentum from the surface to the ocean's interior, creating stratification and new layers with different properties, as exemplified by the breaking of internal waves along the underwater ridges in the North Atlantic Ocean. Upwelling and downwelling. Internal waves cause upwelling and downwelling, promoting vertical mixing that brings nutrient-rich deep water to the surface and transports surface water to greater depths, as exemplified by the tidal-driven internal waves. Shear instability. Internal waves can trigger shear instability, leading to small-scale turbulence and mixing within the water column. For example, Internal waves breaking at the picnic line in the equatorial Pacific create shear instability, influencing heat and nutrient exchange. Turbulence. Internal waves can generate turbulence, promoting mixing on various scales within the water column. For instance, internal waves in estuaries and fjords create turbulent eddies, dispersing nutrients and enhancing mixing in these ecosystems. Thermohaline convection. Internal waves can initiate thermohaline convection driven by temperature and salinity differences. For example, internal waves breaking in the Arctic Ocean contribute to thermohaline convection, influencing sea ice dynamics. Role of internal waves in the facilitation of nutrient transport within the marine environment. Upwelling. Internal waves induce upwelling by pushing deeper nutrient-rich water towards the ocean's surface. This vertical motion enhances nutrient availability in the photic zone, supporting phytoplankton growth and higher trophic levels, for example. Canary current off the coast of northwest Africa. Downwelling. Internal waves also cause downwelling, redistributing surface water to deeper layers. This process influences nutrient transport and affects nutrient availability for marine organisms at different depths, for example, the internal waves of the Gulf of Mexico. Nutrient redistribution. The mixing induced by internal waves redistributes nutrients throughout the water column, enhancing nutrient access for diverse marine communities, for example, the internal waves breaking along the Hawaiian Ridge. Nutrient cycling. Internal waves enhance nutrient cycling within the ocean, promoting efficient nutrient utilization by marine organisms, for example. In the North Sea, internal waves sustain a rich ecosystem with various fish species, seabirds, and marine mammals through nutrient cycling. Internal waves, an enigmatic oceanic phenomenon, remain hidden due to their long wavelengths. Yet, their role in vertical mixing and nutrient transport is vital for marine ecosystems. Unraveling their mysteries can enhance our understanding of ecological processes and aid in preserving marine resources for the future. Q186. Explain the geological mechanism underlying oceanic crust formation at mid-ocean ridges and expound on its profound interconnection with the phenomenon of seafloor spreading. 15 marks, 250 words, core demand of question. Mention about the underlying mechanism of ocean crust formation at mid-ocean ridges. Discuss the relation between the ocean crust formation at mid-ocean ridges and the seafloor spreading. ANS, ocean crust formation, also known as seafloor spreading, is a geological process that occurs at mid-ocean ridges, where new oceanic crust is generated. The formation of ocean crust begins with the movement of tectonic plates. When tectonic plates pull apart or diverge at mid-ocean ridges, magma from the Earth's mantle rises to fill the gap, and a new crust gets formed. The boundary between these plates is referred to as a mid-ocean ridge or spreading center. For geological time scales, this ongoing process of crust formation along with seafloor spreading shapes the ocean basins and plays a fundamental role in plate tectonics and the dynamic evolution of Earth's lithosphere. Following mechanism works for the formation of ocean crust at mid-ocean ridges. Upwelling mantle material. As the plates move apart, the underlying asthenosphere, which is a partially molten layer of the Earth's mantle, is exposed due to the reduced pressure. The reduction in pressure causes the mantle material to upwell toward the surface. Partial melting. As the mantle material rises, the decrease in pressure also leads to a decrease in melting temperature. This causes partial melting of the mantle, forming a partially molten layer called magma. Magma chambers. The melted mantle material accumulates in magma chambers just beneath the mid-ocean ridge. These magma chambers are reservoirs of molten rock waiting to be extruded onto the seafloor. Magma extrusion. Over time, the pressure from the accumulating magma becomes sufficient to breach the oceanic crust above, resulting in volcanic eruptions. The magma erupts at the mid-ocean ridge, creating lava flows. Cooling and solidification. Upon reaching the cold seawater, the erupted lava rapidly cools and solidifies. This process forms new oceanic crust on either side of the mid-ocean ridge. As more magma is extruded and cools, the crust continues to expand away from the ridge. Lithospheric recycling. As the new oceanic crust is formed, the older oceanic crust moves away from the mid-ocean ridge and is gradually consumed at subduction zones, where it is recycled back into the Earth's mantle. Interconnection between the ocean crust formation at mid-ridges and seafloor spreading. Driving force. During seafloor spreading, tectonic plates move away from each other. Magma from the Earth's mantle rises up to fill the gap, and as it cools, it forms new oceanic crust, which further leads to seafloor spreading. Continuous formation. Seafloor spreading is a continuous process that occurs over geological timescales. As the plates continue to diverge, new magma continues to rise, leading to the continuous formation of oceanic crust. Thickness determination. The rate of seafloor spreading determines the thickness of the new oceanic crust. The faster the plates move, the thinner the crust will be. This is because the magma has less time to cool before it is forced to the surface. Age of oceanic crust. The process of seafloor spreading shows that the oceanic crust's age increases with distance from the mid-ocean ridge. The farther away you move from the ridge, the older the oceanic crust becomes. Heat and chemical distribution. The process of seafloor spreading allows for the circulation of seawater into the cracks and fissures of the young oceanic crust. As seawater infiltrates the crust, it interacts with the minerals and rocks, picking up various dissolved chemicals and elements. Similarly, the distribution of heat occurs. Proof. The new oceanic crust is continuously formed at the mid-ocean ridge, and as it moves away from the ridge, it carries with it the magnetic imprints of the Earth's magnetic field at the time of its formation. This phenomenon, known as magnetic striping, has provided crucial evidence for the sea floor spreading. Oceanic crust formation at mid-ocean ridges is a sophisticated geological mechanism, whose continuous growth is driven by the sea floor spreading. Understanding the complex process of ocean crust formation at mid-ocean ridges and its profound interconnection with sea floor spreading is essential for comprehending the dynamic processes shaping the Earth's lithosphere and ocean basins. Q187. Elucidate the role of ocean currents in influencing global climate patterns and their impact on marine ecosystems. 10 marks, 150 words, core demand of question. Explain the role of ocean currents in influencing global climate patterns. Explain both the positive and negative impacts of ocean currents on marine ecosystems. ANS. Ocean currents are the continuous, predictable, directional movement of seawater driven by factors such as gravity, wind, Coriolis effect, water density, and more. They are like giant conveyor belts moving huge amounts of water all the time and affect the climate, weather, and biodiversity of different regions of the world. Ocean currents can be classified based on temperature into warm and cold currents. Cold currents bring cold water into warm water areas, e.g. California current. Warm currents bring warm water into cold water areas, e.g. Brazilian current. Role of ocean currents in influencing global climate patterns. Redistribution of heat and influencing weather patterns. Ocean currents transport heat from the equator towards the poles and vice versa, helping to regulate temperatures across the globe and creating different regional climates. For example, the Gulf Stream carries warm water from the tropical Atlantic to Western Europe, making the climate there milder than other regions at the same latitude. Transport of moisture. Ocean currents also influence the evaporation and condensation of water vapors, which plays a vital role in the global water cycle and precipitation patterns. For example, the Kuroshio current brings warm and moist air from the Pacific Ocean to Japan, creating a humid and rainy climate. Regulate atmospheric circulation patterns. Ocean currents interact with atmospheric circulation, such as the jet stream and the monsoon, creating complex feedback loops that can amplify or dampen the effects of climate change. For example, the El Niño Southern Oscillation, ENSO, is a periodic fluctuation of ocean currents and winds in the tropical Pacific, which affects the weather patterns and climate variability across the globe. Carbon cycle. Ocean currents also play a role in the global carbon cycle by transporting dissolved carbon dioxide, CO2, between the ocean surface and deeper layers. This process affects oceanic carbon storage and exchange with the atmosphere, influencing climate dynamics and ocean acidification. Formation of storms. The interaction between the warm and cold ocean currents can create atmospheric pressure gradients and can contribute to the formation of powerful storms. For example, the hurricanes which occur off the coast of the USA form where Gulf Stream merges with the Labrador Current. Creation of deserts. Cold currents play an important role in the formation of deserts in west coast regions of the tropical and subtropical continents. For example, Peru Current, also called Humboldt Current, is a cold water current of the Southeast Pacific Ocean and a primary reason for the aridity of the Atacama Desert. Climate variability. Changes in ocean currents can lead to climate variability and phenomena such as El Niño and La Niña events. These disruptions can have far-reaching effects on weather patterns, rainfall distribution, and temperature anomalies worldwide. Impact of ocean currents on marine ecosystems. Positive impacts. Transport of nutrients and oxygen. Ocean currents transport nutrients and oxygen from the deep ocean to the surface, or from one region to another, and aid in the growth and survival of marine organisms. Upwelling currents bring cold and nutrient-rich water from the deep ocean to the surface, supporting high productivity. For example, Peru coast enjoys a large fishing industry because of upwelling due to Humboldt Current. Migration and reproduction. Ocean currents provide cues, pathways, and barriers for the movement of marine organisms, which affect their migration and reproduction patterns. For example, salmon use ocean currents to navigate their way from the ocean to their natal rivers, where they spawn and die. Creation of diverse habitats. Ocean currents shape the physical and chemical conditions of the marine environment, which affect the resilience and diversity of marine life. For example, ocean currents can create different habitats, such as coral reefs, kelp forests, and seagrass beds, which host a variety of marine species. Habitat connectivity. Ocean currents connect marine habitats and facilitate the dispersal of larvae, plankton, and other organisms across different regions, promoting genetic exchange and maintaining ecosystem resilience. Marine biodiversity hotspots. Ocean currents contribute to the formation of marine biodiversity hotspots and support a large variety of marine species. For example, the convergence of north equatorial and south equatorial currents in the Coral Triangle encompassing the waters of Indonesia, Malaysia, Philippines, Papua New Guinea, and Solomon Islands has led to an unparalleled biodiversity with a vast array of species. Temperature regulation. Ocean currents regulate seawater temperature, influencing marine species' physiological processes, reproductive cycles, and habitat suitability. Shifts in current patterns due to climate change can lead to habitat loss, species displacement, and ecosystem stress. Negative impacts. Habitat destruction. Strong ocean currents, particularly during storms or extreme weather events, can cause physical damage to marine habitats such as coral reefs, seagrass beds, kelp forests, and result in loss of biodiversity. Invasive species and disease. Ocean currents can facilitate the spread of invasive species and disease among marine ecosystems by carrying organisms or pathogens from one region to another. For example, lionfish, a native of the Indo-Pacific, has invaded the Atlantic and Caribbean water through the Gulf Stream and is posing a threat to the native species. Transport of pollutants. Ocean currents can transport pollutants such as plastics, microplastics, chemical contaminants, and oil spills over long distances, dispersing them throughout marine ecosystems. Plastic pollution, in particular, can have devastating effects on marine life, causing entanglement, ingestion, and habitat degradation. Climate change and ocean acidification. Ocean currents can amplify or mitigate the effects of climate change and ocean acidification on marine ecosystems, depending on their direction and speed. Ocean currents can bring acidic water from the deep ocean to the surface, exposing marine organisms to harmful conditions. Ocean currents play a central role in influencing global climate patterns, atmospheric circulation, and marine ecosystems dynamics. Changes in ocean currents can have far-reaching consequences for both human societies and marine ecosystems. This underscores the importance of monitoring and understanding the complex interactions between oceans and the atmosphere in the context of climate change and environmental conservation. Q188. Examine the intricate interplay between physical processes and climatic factors influencing the genesis and dissipation of oceanic eddies, while assessing their profound effects on marine ecosystems and global climate patterns. 15 marks, 250 words, core demand of question. Explain how interplay between physical processes and climatic factors influences the genesis of oceanic eddies. Explain how interplay between physical processes and climatic factors influences the dissipation of oceanic eddies. Mention the profound effects of oceanic eddies on marine ecosystems and global climate patterns. ANS. Oceanic eddies are like underwater tornadoes. They swirl around and can move warm or cold water across the ocean. For example, Eddies in the Gulf Stream help carry warm water from the tropics up towards the North Atlantic. They're important for ocean health and climate. Interplay between physical processes and climatic factors influences the genesis of oceanic eddies. Ocean currents, strong ocean currents like the Gulf Stream, can create eddies when the flow of water gets disturbed. It's similar to the swirls you see when a fast-moving river hits a big rock. Wind. Wind blowing over the ocean surface can stir the water, creating ripples that can grow into bigger eddies. For instance, when winds from a storm blow over the ocean, they can help form eddies. Water density differences. Eddies can also form when water of different temperatures or salinity, saltiness meet. Tides. The regular push and pull of the ocean's tides can generate eddies. Just as tide changes can cause ripples in a bay or estuary, they can also create larger-scale eddies in the open ocean. El Niño or La Niña. These climate patterns change wind and ocean current patterns. These shifts can lead to more or less eddy formation, depending on the conditions. Ocean fronts. These are boundaries where different bodies of water meet, like warm water meeting cold water. This clash can create instabilities that lead to the formation of eddies. Atmospheric pressure changes. Large-scale changes in atmospheric pressure, such as those caused by moving weather systems, can cause changes in sea surface height, leading to eddy formation. Interplay between physical processes and climatic factors influences the dissipation of oceanic eddies. Friction with seabed. When an eddy encounters shallow waters or an uneven ocean floor, it can slow down due to friction. This process gradually reduces the energy of the eddy, leading to its dissipation. Encountering coastlines. If an eddy moves towards a coast, the coastline can disrupt its circular motion, leading to its eventual disintegration. For example, eddies in the Gulf Stream often dissipate when they hit the eastern coast of North America. Merging with other eddies. Sometimes, when two eddies come close, they can merge into one larger eddy. While this new eddy might be bigger, the overall energy is conserved, leading to the original eddy's dissipation. Heat exchange. Eddies can lose energy through heat exchange with the atmosphere, which can lead to their dissipation. In colder regions, this heat loss can be significant and cause the eddy to break down faster. Wind stress. Strong winds can either aid in eddy formation or contribute to their decay. If winds blow in a direction opposite to the eddy's spin, they can disrupt its motion and contribute to its dissipation. Sea surface temperature. Changes in sea surface temperature, often influenced by seasons or larger climate processes, can impact the stability of eddies and influence their dissipation. Changes in water density. Just as differences in water density can create eddies, changes in these differences, due to warming or cooling, for instance, can destabilize and help dissipate them. Profound effects of oceanic eddies on marine ecosystems and global climate patterns. Nutrient distribution. Oceanic eddies can churn up nutrients from the ocean's depths and spread them around. This is like giving the ocean a big stir, helping feed small plants and animals living in the water. Marine food chain. By bringing up these nutrients, eddies help boost the growth of tiny plants called phytoplankton, the base of the ocean's food chain. This can lead to more fish and other sea creatures in those areas. Heat transport. Eddies help move heat around in the ocean. For example, eddies formed in the Gulf Stream transport warm water and heat from the tropics towards the colder North Atlantic, influencing the region's climate. Carbon storage. The ocean absorbs a lot of the Earth's carbon dioxide, CO2, a greenhouse gas. Eddies can carry this CO2 deep into the ocean, storing it away from the atmosphere and helping to combat climate change. Oxygen supply. When eddies stir up the water, they also bring oxygen down into the deeper ocean. This is crucial for the survival of marine creatures living at depth. Climate buffer. By moving heat and CO2 around, eddies help the ocean act as a buffer against rapid climate change. Without them, Earth's climate could change much more quickly. Marine migration. Some marine animals, like turtles and seals, use eddies as rest stops during long migrations. They're like underwater pit stops, providing a bounty of food for the journey. Going ahead, given the complexity and global scale of these processes, the study of oceanic eddies is of paramount importance for improving our understanding and prediction of climate change and its impacts on marine ecosystems. Q189. Elucidate the challenges posed by the phenomenon of the bomb cyclone. Also, suggest measures to mitigate its adverse effects. 10 marks, 150 words, core demand of question. Discuss the challenges posed by the phenomenon of bomb cyclone. Suggest measures to mitigate its adverse effects. ANS. A bomb cyclone is a large, intense extratropical surface cyclone where the central pressure of a low-pressure system falls by 24 millibars in 24 hours and can result in violent winds developing around the system. For example, a bomb cyclone occurred in March 2019 and affected parts of the central United States. Challenges posed by the phenomenon of bomb cyclone. Severe weather conditions. To exemplify, the bomb cyclone that hit Canada in January 2018 resulted in strong winds exceeding 70 miles per hour, 113 kilometers per hour, leading to widespread power outages and travel disruptions. Coastal flooding. Hurricane Sandy in 2012 intensified into a bomb cyclone, resulting in significant storm surge and devastating flooding along the U.S. East Coast. Heavy snowfall. The bomb cyclone that struck Canada in March 2019 caused blizzard conditions and brought several feet of snow to certain areas. Environmental damage. For example, the intense storm surge associated with bomb cyclones can erode beaches and destroy habitats along coastlines, impacting marine and terrestrial species. Impacts on agriculture. The 2019 bomb cyclone in the U.S. Midwest caused significant losses for farmers, including damaged grain silos and livestock fatalities. Measures to mitigate its adverse effects. Early warning systems. Implement robust meteorological monitoring systems to detect and predict bomb cyclones. For example, the National Weather Service in the United States issues alerts and warnings to the public. Emergency response plans. For instance, local authorities can establish designated evacuation routes and shelters in coastal areas prone to bomb cyclones. Public awareness campaigns. To illustrate, community outreach programs and media campaigns can raise awareness and prepare the public for them. Resilient building codes. Implement stringent building codes that require structures to withstand high winds and heavy precipitation. This includes using impact-resistant windows, reinforced roofs, and proper drainage systems. Research and development. This includes studying atmospheric dynamics, climate change impacts, and developing advanced modeling techniques to enhance forecasting accuracy. Coastal protection measures. Construct or reinforce coastal defenses such as seawalls, breakwaters, and sand dunes to mitigate storm surge impacts during bomb cyclones. Thus, by implementing these measures, countries can better manage the challenges posed by bomb cyclones, minimize the risks to human life and infrastructure, and facilitate a more effective response to these severe weather events. Q190. Describe the natural and anthropogenic factors that affect the salinity budget of ocean. 10 marks, 150 words, core demand of question. Provide the factors that affect the salinity budget of oceans. Natural factors, anthropogenic factors. ANS. The salinity budget of oceans refers to the quantification and analysis of the processes and mechanisms that influence the distribution, variation, and maintenance of dissolved salt content within seawater across global marine systems. It is affected by natural as well as anthropogenic factors as explained below. Factors affecting the salinity budget of oceans. Natural factors. Evaporation and precipitation. Evaporation removes fresh water from the oceans, increasing salinity, while precipitation adds fresh water, decreasing salinity. For example, the Red Sea has higher salinity due to high evaporation rates and limited freshwater inflow. River discharge. The influx of freshwater from rivers dilutes seawater, reducing salinity near river mouths. For example, the salinity of the Baltic Sea is lowered by the input of freshwater from surrounding rivers. Sea ice formation and melting. During sea ice formation, salt is excluded from the ice, increasing the salinity of the surrounding seawater. When sea ice melts, it releases freshwater, decreasing salinity. The melting of polar ice caps contributes to freshwater input. Ocean circulation. Ocean currents can transport water with varying salinity levels across vast distances. Regions where warm currents meet cold currents can experience differences in salinity due to water temperature variations and mixing. For example, the Gulf Stream in the Atlantic Ocean, which influences salinity patterns along the U.S. East Coast. Ocean mixing. Vertical and horizontal ocean mixing processes redistribute salinity. Upwelling, where cold, nutrient-rich waters rise to the surface, can bring higher salinity waters to the top, influencing local salinity patterns and marine life. For example, the coastal upwelling along the west coast of South America is an example. Temperature variation. Temperature affects water density, influencing salinity. Warm water holds more dissolved salt than cold water. For example, in regions with high temperatures and high evaporation rates, such as the Persian Gulf, salinity tends to be higher. Submarine hydrothermal venting. Deep-sea hydrothermal vents release mineral-rich fluids into the oceans. These fluids can contain high concentrations of dissolved minerals, impacting localized salinity levels. For example, hydrothermal venting along the mid-Atlantic ridge contributes to the unique salinity and chemical composition of the surrounding deep-sea water. Anthropogenic factors. Desalination. The process of desalination involves removing salt from seawater to obtain freshwater. While this provides a freshwater source, it also concentrates the remaining seawater, increasing its salinity. For example, desalination plants in the Persian Gulf have contributed to local increases in salinity. Industrial and agricultural runoff. Human activities, such as industrial processes and agriculture, can introduce pollutants and excess nutrients into coastal waters. This can alter salinity levels through changes in freshwater runoff patterns. For example, the Dead Sea's salinity has been affected by human diversion of its tributary rivers for irrigation. Coastal engineering. The construction of dams, canals, and other coastal engineering projects can alter the flow of freshwater into the ocean, affecting local salinity patterns. For example, the Aswan High Dam on the Nile River has reduced sediment and freshwater discharge into the Mediterranean Sea, impacting its salinity balance. Marine pollution. Pollutants such as plastics, chemicals, and oil spills can disrupt the balance of marine ecosystems, potentially impacting salinity through the introduction of foreign substances. For example, oil spills in the Gulf of Mexico have altered the salinity levels in affected areas due to the dispersion of oil and mixing with seawater. Climate change. Climate change can influence ocean salinity through changes in precipitation patterns and sea ice melt. Rising temperatures can lead to more evaporation and altered rainfall distribution, affecting regional salinity levels. For example, the Arctic Ocean has experienced reduced sea ice, contributing to fresher surface waters. Ocean salinity encapsulates the fragile equilibrium between nature and human factors. However, escalating anthropogenic disruptions are jeopardizing this equilibrium, emphasizing the imperative of environmental action. By adopting sustainable measures, combating pollution, and addressing climate change, we can collaboratively restore oceanic salinity balance and foster a harmonious coexistence between the natural world and human society. Q191. Discuss the difference between tropical and temperate cyclones. Explain the conditions favorable for the formation of tropical cyclones. 10 marks, 150 words. Core demand of question. Discuss the difference between tropical and temperate cyclones, and explain the conditions that are favorable for the formation of tropical cyclones. ANS. Cyclones are dynamic low-pressure weather systems characterized by isobars indicating a gradient of increasing pressure outward. Forming primarily over tropical and temperate oceanic regions, they bring heavy rainfall, fierce winds, dense cloud cover, and electrical storms. Commonly known as atmospheric disturbances, cyclones pose significant meteorological challenges and can lead to severe impacts on affected areas. Difference between tropical and temperate cyclones. Form in tropical regions. 5-25 degrees. They generally originate in tropical regions between latitudes 5 to 25 degrees. Thermal origin due to the warming of the sea surface. They derive their energy from the warm surface waters of the ocean, where heat transfer from the ocean to the atmosphere initiates their formation. Very violent in nature and have high-velocity winds. They are characterized by their extremely strong winds, often exceeding speeds of 250 kilometers per hour. Low pressure, around 880 MB, they are associated with a central area of low atmospheric pressure, typically around 880 millibars, which contributes to the inward spiraling winds and intensifies the storm system. Originate over oceans but die out on land. They generally form over warm ocean waters, but lose their energy source upon making landfall. They often track from east to west, bringing destructive winds, heavy rainfall, and storm surges, especially affecting coastal regions. For example, Cyclone Maikwang led to torrential rains, flash floods in Tamil Nadu. Occur in late summers. They are most prevalent during late summer to early autumn months, typically occurring between August and October when ocean temperatures are at their warmest, providing optimal conditions for their development. Temperate cyclone. Form in temperate regions. Extratropical cyclones form in temperate regions, 40-65 degrees, and are known as frontal cyclones, originating along frontal boundaries. Less destructive and low velocity. These cyclones are less destructive and feature relatively lower wind velocities, typically exceeding 150 kilometers per hour. Low atmospheric pressure. They are associated with a central area of low atmospheric pressure, typically around 990 millibars. Predictable. They are predictable and form along the westerlies, traveling from west to east across the globe. Occur in winters. They primarily occur during winters, causing disturbances in the westerly wind patterns, influencing weather conditions. Favorable conditions for the formation of tropical cyclones. Good source of latent heat. Ocean waters having temperatures of 27 degrees Celsius or more is the source of moisture that feeds the storm. The condensation of moisture releases enough latent heat of condensation to drive the storm. Coriolis force. The Coriolis force at 5 degrees latitude is significant enough to create a storm, cyclonic vortex. About 65% of cyclonic activity occurs between 10 degrees and 20 degrees latitude. Low-level disturbances. Low-level disturbance. Thunderstorms, they are the seeds of cyclones, in the form of easterly wave disturbances in the intertropical convergence zone, ITCZ, should pre-exist. Temperature contrast between air masses. The convergence of air masses of different temperatures and the resulting instability are the prerequisites for the origin and growth of violent tropical storms. Wind shear. Tropical cyclones develop when the wind is uniform. In the temperate regions, wind shear is high due to westerlies, and this inhibits convective cyclone formation. Upper tropospheric divergence. A well-developed divergence in the upper layers of the atmosphere is necessary so that the rising air currents within the cyclone continue to be pumped out and low pressure is maintained at the center. Humidity factor. High humidity, around 50 to 60%, is required in the mid-troposphere since the presence of moist air leads to the formation of a cumulonimbus cloud. Thus, tropical cyclones play a crucial role in redistributing heat and moisture globally, impacting weather patterns and replenishing freshwater resources, whereas temperate cyclones influence mid-latitude weather systems, contributing to rainfall, snowfall, and temperature variations. Both cyclone types are vital for climate regulation, weather prediction, and ecosystem health.